So good morning, good afternoon, and good evening. Thank you all very much for joining us. So my name is Evgeny Stadnik, and I'd like to welcome you to our session on precision tests, which we're organizing together with Victor Flambaum. So basically, our session is going to cover recent developments and progress in a few topics. So these are basically variations of the physical constants of nature, tests of the fundamental symmetries, and also how we can probe more general models of the dark sector. Before we continue to the talks themselves, I'd just like to make a few general announcements. First of all, I would like to let you know that all sessions of this year's Marcel Grossman meeting are recorded. Also, if you're not in the process of giving a talk or asking a question, could you please keep your microphone muted and video switched off? And finally, since we have a fairly tight schedule today, I'd like to propose that we reserve the questions for the ends of the talks. And if there's time remaining at the end, we can also have, in principle, a lengthier discussion at the end of all of the talks. And so without further ado, I'd like to introduce our first speaker, Dionysis Antipas. So if you'd like to share your slides, please. Oh, perfect. And the topic of your talk today is precision isotope shifts in ytterbium applications for new physics. And I forgot to mention that, of course, Dionysis is from mine. So please start.
Now you can probably hear me fine, right?
Sorry, I meant to say, yes, we can hear you now. Sorry, my microphone was muted.
Okay. So now I just realized I appear as some other person. I appeared as Shu Zhang, but that's probably fine, right?
That's okay, but we can't see your slides anymore.
Yeah. I need to, sorry, just give me a second here. Okay. Somehow I suddenly lost control of this Zoom, so I don't see buttons anymore. Sorry about this.
Maybe maybe we can try unsharing screen and then sharing again.
But can you see? You don't see screen. You don't see anything right now. Sorry about this.
Can you unshare the screen and then reshare it?
No, I don't see. Somehow I lost all the buttons here.
Oh, okay. Okay. In that case,
maybe
let me do it like this. Okay, so we'll manually do this.
Now it's
okay. Now could you try sharing it again?
Okay. So now you can hear me and you can see my slides.
I can see you and hear you, but I cannot see your slides.
Okay. Now you might.
Perfect. Good. Now I can see your slides.
All right. So let's hide all the stuff from here. All right.
Oh, perfect. Whenever you're ready.
Okay. Sorry about the small mishap. Yes, thanks to the organizers for the invitation and the opportunity to talk about a running project that we have here in Mainz. This is on precision isotope shifts in ytterbium, and this relates to searches for new physics. So on the experimental front, the project takes place at Helmholtz Institute Mainz, and this is mainly the work of Nathaniel Figueroa, a student. And we have theory support by Julian Beregut, Vladimir Zuba, and Victor Flambaum, so this is a collaboration. Right, so what we are doing in this project is to search for light force mediators between the electron and neutron. So we are searching for new physics, which is described by this Yukawa type potential here that basically describes the exchange of a new boson, massive boson of spin 0, 1, or 2 between the electron and neutrons. and M phi sub phi here is the mass of the boson, and A new physics here is the new coupling, new physics coupling constant, which is analogous to the fine structure constant for the electromagnetic interaction. So this is a spin-independent potential. We are mostly sensitive in the search for light massive bosons. That means that the boson has to be less than this 100 MeV, or equivalently has to be the Compton wavelength, or the interaction length has to be greater than the size of an atomic nucleus. One approach to do this search would be to measure an atomic parameter, such as an atomic transition frequency, very precisely and compared to theory. However, for the most interesting atoms to measure here, theory is not precise enough. And so a single isotope measurement in search of such a new boson would not be competitive. So it was proposed, instead of looking at a single isotope, is to look at the chain of isotopes. And so in particular, one can look at a series of isotope shifts in a chain of isotopes in two different atomic transitions. And it's well known that at least to first order, this isotope shifts in one atomic transition of some element versus the shifts in another transition of the same element are linearly correlated. So that's the King linearity, or King plot linearity, for which I'm going to discuss further in the next slide. But the idea is to look for deviations from nonlinearity and do so in a way that avoids the need for high precision atomic theory. So it's a data-driven approach. So this was a proposal that came out in 3 years ago in 2018 by Julian Beregut, Dimitri Butker, Victor Flambaum, Gilad Perez, and others. Right, so here the idea is again to compare isotope shifts in different transitions of the same element in this so-called King plot analysis. So let's see what the King plot is. Suppose you have an atomic transition indicated here by A. You can write down the isotope shift for this transition here, where I and J now represent different isotopes as a sum of two terms, where the first term is a so-called mass shift, and the second term is the field shift. Each of these two terms is factorized as a product of a term that does not depend on the isotope, but depends on the transition, times a term that is basically a nuclear parameter. K and F here are atomic parameters, and mu and delta R square are nuclear parameters. Mu is the inverse mass difference between two isotopes, and delta R square is the RMS squared difference, RMS radius squared difference between the two isotopes. So that's these are the two primary contributions to the isotope shift. And now if two transitions are considered, one can solve for delta R squared and eliminate between the two equations and obtain this so-called modified isotope shift. So this is the nu over mu for one transition versus the other. And that's, as you can see here, there is linear correlation between these two that can be plotted to obtain a so-called King plot. And to first order, there is linearity here. And this linearity occurs as long as the isotope shift can be written as factorized as a product of parameters that depend on the nucleus times parameters that depend on the atom, but yeah. How can we break this King plot linearity? Well, we have to consider additional terms. So aside from the primary terms I talked about, the mass shift and actually the first order field shift, one can consider additional contributions such as the quadratic field shift and a higher order effect that depends on the nuclear deformation that is influenced by the nuclear deformation of a nucleus. And of course, since we are looking for new bosons, we can consider an additional term related to new physics, where delta here is delta alpha is some atomic parameter for the transition alpha, and A and delta N is the difference in the neutrons between two isotopes labeled by I and J. So we can consider these additional terms, and we can actually write this down for two different transitions, A and B as before, and eliminate delta, the primary parameter related to the nuclear radius to obtain this equation here, which is rather long. And the first line here is what I showed before. It's responsible for the King linearity. However, there is additional contributions here in lines 2, 3, and 4 may cause deviations from non-linearity. So the essence of the proposal by Berengut and others is to make measurements of different transitions. And if non-linearity is observed, one can constrain new physics indicated by this last term here, assuming that there are no nuclear effects that can also cause non-linearity and mask perhaps new physics. So the method does not discriminate between standard model subdominant nuclear effects from new physics. So in the absence of these non-nuclear physics effects, one can again constrain new physics. To do this search, one needs to have a chain of isotopes. So to observe non-linearity in the King plot, one would need to have at least 3 data points, so at least 4 isotopes. And one would also like to have narrow transitions because these are more easily measured precisely. So after the seminal proposal by Berengut and others, several experiments were started to provide high precision isotope shift data in search for new physics. And there is a series of publications. The most notable ones come from an experiment in calcium clouds and another one in ytterbium plus that were actually published together last September in PRL. The calcium experiment by the group of Michael Drusen in Aarhus, and the ytterbium plus experiment by the group of Vladan Vulevich at MIT. And you see here, this was in the news, and the reason is because one experiment saw hints for new physics, the other did not. So what we see here is on the left plot, actually in the inset of the left plot, we see a King plot, and that's nice and linear. But now if we zoom in, we see deviation from linearity. So these are data for the ytterbium plus experiment, and authors claim a 3 sigma deviation from a non-linearity that can be interpreted as new physics or as higher order contribution to the field shift. On the other hand, the calcium plus experiment did not observe non-linearity. So you see the King plot here. If you zoom in, the data points are within 1 sigma or so fall within the straight line. So it's a bit intriguing that one experiment saw non-linearity, the other did not. And although both experiments have similar sensitivity in constraining new physics, so that's interesting to investigate further. And so that was done on the theory front by Vladimir Zuba and Victor Flambaum and others. This was a paper which was published actually a few months ago, in which authors studied the higher order contributions to the isotope shift in the ytterbium plus transitions. And as they point out, it's likely that the isotope shift, the King plot nonlinearity observed in the ytterbium plus experiment can be interpreted due to this higher order term in the isotope shift related to the influence of the nuclear deformation of the ytterbium nucleus. So the quadratic field shift, as pointed out in the experimental paper on the ytterbium plus experiment, is unlikely to be a major contributor to the nonlinearity. Right, but there is more to this story in terms of theory and formalism. About 6 months ago, a new theory proposal came out that essentially proposes to generalize the King plot analysis through the inclusion of more than 2 transitions. So instead of analyzing together 2 transitions of some element, include data from multiple transitions, and that has the ability to separate subdominant nuclear physics effects from potential new physics. So if one, instead of 2 transitions, has m transitions in this multidimensional King analysis, then it turns out that m-2 subdominant nuclear effects can be accommodated. And it's also possible to mix measurements made in both ions and neutrals, and that provides flexibility for experimentalists. Right, so that's here in Mainz we have an apparatus dedicated for atomic particle violation studies using ytterbium. So we decided to use the atomic beam apparatus to make measurements in neutral ytterbium in a single transition and add this to the existing data, add this data to combine this data with the data in the ytterbium plus to employ the generalized King analysis. That's also good because we can, through this generalized King analysis, we can validate the 3 sigma observation of new physics in the ytterbium plus experiment. It's also good from a theory point of view to provide more data because then theorists can check their models and try to understand the nuclear physics contributions to the isotope shift interaction better. Right, so we are doing here spectroscopy on the ytterbium ground state. That's a singlet S to the excites, and we excite atoms to the excited state singlet D2. We do this as a 2-photon transition. So the lifetime of the excited state is narrow. So we have a narrow transition that's good to measure. So it's a 2-photon transition that we excite, and then we detect fluorescence in the second path channel of the decay path back to the ground state. This is fluorescence collega 399 nanometers. So this is a schematic of the atomic beam apparatus here. So we have an atomic beam, and we shine a laser beam, actually with the use of the Fabry-Perot cavity to excite this 2-photon transition. And actually what happens here is that it is the counter-propagating components of the light circulating this Fabry-Perot cavity that are responsible for this Doppler-free excitation. So that has certain advantages, that it suppresses Doppler broadened backgrounds and so on. And we make measurements using all available spinless isotopes of ytterbium. We don't want to work with the spinful isotopes because then it becomes challenging to separate the hyperfine interaction contributions from the isotope shift. So we limit our studies to the 5 available spin zero isotopes. And the goal in this experiment is accuracy in a single isotope shift measurements on measurement of the order of 300 Hertz. This is to match the accuracy achieved in the ytterbium plus experiment. Now, how do we make these measurements? So we want to keep this simple, avoid issues with calibration of the laser frequency and so on. So what we do is that we use multiple different laser frequencies to excite different isotopes. And so through phase modulation, we put so-called frequency sidebands to our main laser beam. So these new frequency fields are precisely spaced by some well-controlled frequency nu RF by the main laser field. And so if we tune the main laser frequency, the primary laser frequency and the nu RF appropriately, then we can have simultaneous excitation of 2 isotopes. So the goal of this experiment is to determine the frequency nu RF that results in simultaneous excitation of 2 isotopes, and that's related to our isotope shift measurement. Because it's a 2-photon transition, in fact, the isotope shift is then twice this nu RF frequency. Right, so we want to excite 2 isotopes simultaneously, but that kind of contradicts the point of detecting them separately. So we really want to detect them separately so we can fit in individual line shapes to the 2 isotope spectral profiles. And we are lucky enough that the Fabry-Perot cavity does this for us. So what you see in the upper plot is a simulated spectrum of the Fabry-Perot cavity transmission as we change its length rapidly. So you see that the different frequencies of our laser field resonate at different times. And as I mentioned before, if we adjust the mean laser frequency nu L and the RF frequency nu F appropriately, then we get a condition so that we can excite the 2 isotopes together. But because the different frequencies resonate at different points, then we have this consecutive fluorescence spikes for the different isotopes as we slowly scan the laser frequency. So that allows us to kind of together but separate excite the 2 isotopes and obtain individual line shapes. And this is what these line shapes look like. So I mentioned that the natural line width is narrow for this transition. However, we observe a line width which is near a megahertz, and that's unfortunately limited by transit time of atoms through our atomic beam. Nevertheless, with enough signal collection, we can get enough statistics and narrow down the isotope shift measurements to get our 300 hertz goal in statistical accuracy. Right. So again, the goal of the experiment is to determine the spacing between our phase modulated laser fields that result in simultaneous excitation of two isotopes. Now we have to be very careful with ensuring that we excite the two isotopes with equal powers. If not, then there is a AC Stark shift in the measurement that can really throw us off. So we try hard during the measurement to excite two isotopes with fields that have equal amplitude. In addition to this, we record the residual imbalance between fields, optical fields exciting different isotopes, and include that in the analysis. And so we interpolate measurements of the isotope shift for zero imbalance. So with this interpolation, that ought to be enough to kill any residual AC Stark effects. However, it's possible to have kind of hidden AC Stark contributions in the cavity. That happens when higher order cavity modes are parasitically excited and interfere with the primary cavity modes to induce interference that effectively results in different power experienced by different isotopes. So in the end, the way to go about solving this issue is to take data at different powers and then extrapolate the isotope shift at 0 powers. And that actually seems to be very clean in terms of residual AC Stark effects, because we measure slopes in this plot here, which are consistent with 0 within our measurement accuracy. So that's the main systematic effect that we have. Here's another one that's actually more severe in terms of the time it takes to handle it, and comes because of spectral imperfections in the Fabry-Perot. So the Fabry-Perot cavity is supposed to enhance one field, but suppress the others. However, this suppression is imperfect, so a little bit of off-resonant frequency components, unwanted ones, exist in the cavity in addition to the resonant one that excites our isotope. And so one of these components combined with the resonant component results in parasitic excitation of an unwanted isotope within the detection channel of the isotope that we seek to measure. So for example, if we measure signal shown in blue here by some isotope, then we get a little bit of background from another isotope. And when we go measure the other isotope, we get a little bit of background from the first isotope, the blue isotope. So we really have to measure these backgrounds carefully and subtract them from our line shapes. And this is data showing in green primary signal from an isotope, and in blue and red how that isotope is detected parasitically in other detection channels. So these backgrounds are on the order of 0.1% to 0.5% of the main signal, and eventually, with quite a bit of effort, we account for them, and so we are not limited in the experimental accuracy due to this background. But this is in fact the main systematic effect that we have to deal with in this experiment. Eventually, we are statistics limited, so and there is of course a number of other systematics to consider, but we account for them properly, and eventually we are statistics limited in our measurements for the isotope shift on the neutral transition, and then we can plot this.
10 minutes to go. 10 minutes to go. Yeah.
How many? Sorry.
10 minutes to go, including time for questions.
Okay. Okay. Right. And so what I'm showing here is the main result of this work, which is a King plot combining our data on the y-axis on the neutral transition with data on one of the transitions of the measured the interbeam plus experiment, and you see the nice linearity in the King plot. However, zooming in by 10 to the 6 times reveals a large non-linearity, which is actually 10 times about 4 times greater, in fact, for 2 of the data points compared to that seen in the interbeam plus experiment. Now, Vladimir Zuba and Victor Flambaum have provided calculations that help us interpret this non-linearity. So the interpretation is favors the influence of the nuclear deformation on the isotope shift. Now, what's next in this work is to apply the generalized King analysis. So we will combine our data with the data on the two ytterbium plus transitions and try to separate new physics from non-nuclear effects. This is work in progress. I can, as a preliminary finding of this work, which is not yet complete, I can report that the 3 sigma hint of new physics in the ytterbium plus experiment seems to be now reduced to 2 sigma. So that tends to favor interpretation of the nonlinearity in the previous experiment as nuclear physics and not as some new physics effect. Right, maybe I can skip the outlook and go to the summary. And so we measured the isotope shift on a chain of 5 ytterbium isotopes on a narrow transition in ytterbium. We saw a large nonlinearity when combining our data with existing data on the ytterbium plus ion. Large nonlinearity, I mean the King plot. This is likely to be caused by the influence of nuclear deformation on the isotope shift, specifically on the field shift. And now we are working doing generalized King analysis in order to interpret the observed nonlinearity, and we'll see what happens with this. So thank you very much for your attention.
Well, thank you very much, Dionysus, for the nice talk. Questions, please. If you have questions, you can either use the reactions tab where there's raise hand, or you can type your question in the chat. Yes, Sebastian, please.
One question. You have said that you think that these results were because of nuclear deformation. But if it were because of a new particle, what would be its mass?
So the mass of the particle, so that's a parameter in the search. So we don't know what is the mass, but we know, for example, maybe I should go to a plot showing projected constraints. So the particle mass can be anything. There is sensitivity if the Compton wavelength is greater than the atomic nucleus size. So the mass has to be, we have sensitivity if the mass is smaller than 100 mega eV. And so the sensitivity gets best for light masses. So below kV or less. So what's shown here is projected couplings for different future experiments reaching different accuracies in the isotope shift. So the interesting parameter space shown here is EV to 100 mega eV or so.
Okay, so this plot is from your experiment?
This plot is from this original proposal by Berengut and others. So these are projected constraints. So once we have finished the generalized King analysis, then we will be able to place new constraints here. Constraints were also placed by the ytterbium plus and calcium plus experiments, but I haven't shown them here.
Great, thanks.
Any other questions? In that case, Eckhard, please.
Hello, I like to talk, but I wanted to ask a question. So I'm just speculating. So you mentioned that you focus on the even isotopes, but there is isotopes with hyperfine structure, where the hyperfine structure can be measured in principle also quite precisely. As I'm saying, I'm really speculating. Wouldn't it even maybe help to take one of those isotopes into account, doing the hyperfine correction, especially if there is about subtleties of the nuclear structure? Would it be more interesting to have an isotope with a non-zero spin in the analysis?
Right. So I guess the answer here depends on. There is discussion about this. So different people tell you different things, yes or no. My understanding about the hyperfine interaction effects is that so that also requires calculations. And so the accuracy, it might get hard to separate the hyperfine interaction effect from the isotope shift. That's my understanding of it. So we avoid working with the spinful isotope. It seems challenging to separate.
Thank you.
We have time for, I think, one more question. Well, in that case, is there, do you know, Dionysus, if there's, for example, a possibility of some orthogonality with the new physics models in terms of maybe an effect can be seen in a terbium ion and not seen in calcium ion, or in different species altogether? Has that possibility been investigated?
So as far as I understand, the modeling is done in terms of in terms of this effective spin independent effective potential, Yukawa potential. Unless atomic theory somehow enhances or suppresses the effect in different elements, I think it should be visible in any element. I don't see some reason why it should have suppression in some atom. What changes, of course, is the neutron number, right? So these heavier atoms are better for this. So the method itself has this issue that it doesn't separate nuclear effects from new physics effects inducing nonlinearity. So in that sense, you would like to use a light atom because then the field shift is smaller, and so the associated higher order effects with the field shift should also be smaller. So heavy atoms are good, but light atoms are also good in that regard. So yeah.
Thank you. Let's thank Dionysus, and our next speaker is Ariel Chudnitsky. Ariel, if you would like to share your screen, please.
Can I share the screen now? Yeah.
Yes, please. Yes, we can see your slides. Would you like to do full screen?
Can you see it?
Oh, perfect. We can see it. Yes, and just as a reminder, if you're not currently giving a talk or asking questions, please keep the microphone muted and video switched off. Thank you. Whenever you're ready, Ariel.
Okay, very good. Thank you. Thank you for inviting me. And probably my talk will be a little bit different from most of the talks. I will be talking about the fundamental physics, and I have the title Dark Matter Baryogenesis. But the most important part for this session probably is a possible future tests. So essentially, we need some kind of precision to study something what I am about to say. So, and this talk is mostly based on a couple of recent papers written with different people, including Butker and Flambaum, and two other papers to mention that it is not just a single manifestation of something new phenomena I want to discuss. There are many, many others. And that's exactly my goal, to demonstrate that it is a very, very generic phenomena I'm talking about. But before I discuss about the tests, let me say about the essence of the model. So essentially the conventional wisdom that is that we definitely have a dark matter. We know about that for many, many years, and we definitely know about baryogenesis. We definitely know that we do have baryons and not so many antibaryons in our universe. There are many other observed puzzles, fundamental puzzles. And the way how I see it, it is just two sides of the coin. So it is a dark matter side of the coin, and this is a baryogenesis side of the coin. Again, that's something very fundamental, and most of you have studied this in a graduate school. So naively, it's considered as two completely different stories. So essentially, what we want to argue is that it is a one and the same story. And we want to test this idea that it is a one and the same story. So, and I specifically discussed today about some mysterious seismic and infrasonic events which have been observed. And in addition to that, I will be talking about some shortly, very briefly, about mysterious telescope array bursts, about Anita anomalous event, to demonstrate that essentially it is an extremely generic, something is happening which is a very, very hard to understand from the conventional physics. Before I do that, I want to explain what this model is about. So, in a what sense, it is a two naively different story. So naive idea about dark matter that it requires definitely fundamental new fields. And basic paradigm today is a WIMPs. Basic and most general accepted paradigm is a WIMPs. Another moral that new fields must be non-baryonic. Why is that? Because we definitely know that it must be actually completely decoupled from radiation, dark matter radiation, from CMB, from Big Bang nucleosynthesis and stuff like that. So essentially, this proposal is dramatically different, fundamentally different. So instead of new fields, we are talking about new phases. There is so-called color superconducting phase in quarks and gluon plasma in the QCD, is better to say. And it is very similar to conventional superconductor, but not with electrons, but with quarks. And instead of baryogenesis, we are not talking about the producing of baryons, we are talking about separation of them. Parameter theta, which is related to the axion field, essentially it is the axion field. It plays extremely important role. Okay, now the idea that dark matter could be actually dense, very dense quark nuggets of the standard model, no new field, was formulated long, long ago by Vito. Because for cosmology, the most important part, it is not just new field. The most important part which enters all the cosmological astrophysical computations. It is a cross-section divided to the mass. And as long as it's much, much smaller than conventional, what is a conventional for standard physics, hadronic physics, we know, it is okay. It's considered as an absolutely dark matter. Why? Because it's completely decoupled from the from everything what I already mentioned, Big Bang nucleosynthesis, from cosmic microwave background and stuff like that. However, people discovered many problems with the original Witten's idea. So the new element here, fundamental new element, which was not available at that time, is an axion field, and we call this object axion quark nuggets. Okay, so AQN for short. So, and one short remark that there are two different but fundamental additions to the conventional Witten's case. There are the main walls, so-called n equals 1, where you have one and the same vacuum state. It does not play much role today. But what is important today is that it could be nuggets and anti-nuggets. Nuggets which made of matter and antimatter. Because it's separation of charges, it's not producing of the baryon charge. The most important part here is that it definitely qualified as a dark matter candidates, exactly as in Witten's case. And what is important here, that so-called CP-odd axion field generate disparity between two species. It is a CP violation and C violation, and theta equal non-zero. And that's absolutely fundamental reason why dark matter or visible matter are more or less the same order of magnitude. It does not depend on the axion mass at so-called initial theta parameter, because all parameters are proportional to one and the same fundamental QCD fundamental scale. And we know that actually visible universe is proportional to lambda QCD. And Higgs boson, for example, has nothing to do with that. Proton mass, it's mostly lambda QCD. It's QCD physics, not quark mass. Now, let me show precisely, not precisely, but not in scale, how these nuggets look like. So the idea why they're absolutely stable object, because there is a Fermi pressure here from inside, there is an axion domain wall outside. It is an antimatter. It could be matter exactly in the same way. There are many different emission, but the most important part that it must be large. As long as it is a large, it's definitely decoupled, because number of these guys is extremely small, so essentially they don't interact with the conventional matter. Now the main part of my talk, that essentially that there are some mysterious explosions. So it's applications of this idea. There are some mysterious explosions. They have been known for centuries. They are so-called quakes. In different countries, they call in a different way, in their different languages. So essentially what we advocate an idea that it is a manifestation of antiquark nuggets when they entering Earth's atmosphere. There are many observations by people, but I cannot just turn on TV and discuss what actually they have seen. Fortunately, one event which occurred in 2008 was properly recorded by infrasound array and by seismic stations as well in Ontario, London. What is important, normally if it is a normal meteor, in this case, people definitely have so-called sky camera network, and they definitely see some kind of correlation. Now, it was not a single hint that there is actually meteor, because it was absolutely not observed by all sky camera, which was in place. And seismically, it was also supported that they have seen something. Okay, let me show where it happened. It happened somewhere here. Sorry, it is a station, infrasound station, and they estimated it happened somewhere here. And this one, it's many different seismic stations. What they observed infrasound event, and this is audible. So essentially, it is correlated with audio signal and seismic signals as well. And this is different seismic signals from different stations that have been also observed. So now come to the idea what's actually happening from Nugget's viewpoint. So essentially the idea that we definitely can compute the flux, because essentially it's given by the dark matter. So just raw dark matter enters this formula. Important part that, again, can be computed, spectrum can be computed, and it mostly in X-rays, and there is no visible light, and that's, I'll show the spectrum in a second. Idea is the following, that X-rays will be quickly absorbed on a scale, mean free path scale is 5 meters or so. And some portion of X-rays will be generated shockwave. It's very similar to what conventional bomb blast happens when you have a much lower frequency spectrum photons and a huge atomic photoelectric effects with a huge cross-section. That's different because it is X-rays and not visible, not UV, but nevertheless, the idea that blast or shockwave happens is about the same. Now, that's the spectrum I promised to show, that essentially because of plasma frequency, there is no visible light whatsoever. Now, the difference between a conventional spectrum and spectrum related to the quark nuggets, it leads to dramatic observational differences. They are not accompanied by the visible light, which normal meteors do, and the frequency of infrasound, it's much lower than the conventional frequency. It is a 5 hertz, which is definitely in the infrasound part. And the reason for that, because the mean free path is much, much larger than the conventional one. And overpressure also can be estimated. It's on the level of 0.3 Pascal. So all these observations are very, very close to actually infrasound station recorded. Now, the part which is important here, that nuggets could be in different sizes. I didn't discuss it here, but essentially it is distributed in some way. The conventional average, which I mentioned before, on the level 10 to 25, now it's must be much, much larger to produce the intensity, which is relatively large. So that's exactly the reason why it is a very rare event. It happens once every 10 years instead of happening very often. So proposal, which is important probably for this community, that essentially how to measure conventional small nuggets which produce not so intense effect, huge effect. And the idea in our paper with Butter and Flambaum was that essentially distributed acoustic sensing can be installed exactly in the same area, or in any area where you have all sky camera, such that it can be actually measured. Okay, so that's exactly the idea. Now, I want to discuss completely different case, such that you would not have impression that the reason why I'm talking about I specifically developed this model in order to explain one single effect. It's not the case, actually. The idea to develop this model was that dark matter and visible matter are very similar in density. That's exactly the main motivation. Now, I want to discuss about completely different event which was observed, and it does not have conventional or simple explanation. Let me explain what effect mysterious burst I'm talking about. Normally, you have some kind of cosmic rays, and cosmic rays, they come here or there, and definitely they don't come very often, especially intense effect. But this was a clustering puzzle effect, such that you have a cosmic-like event within 1 millisecond and 3 consecutive events, one after another, and all of them in the same area, 1 kilometer area. If one tries to treat or interpret as a conventional cosmic rays, in this case, one should expect extremely lower, not extremely low energy, 10 to 13 eV, while intensity suggests 10 to 19. And the difference in the event rate is unbelievably huge. That happens once every 10 years, and this happens milliseconds. So there is another puzzle, so-called curvature puzzle. I'll show a few slides below. Curvature puzzle that essentially it's much more curved. And synchronization puzzle. Again, somehow these events are correlated or synchronized with the thunderstorm. Again, how do thunderstorm or cosmic rays know about thunderstorm? Nevertheless, it is correlated. But sunbursts are not related to lightning at all. Okay, so let me show precisely what they have seen. So that's a burst event when you have absolutely huge curvature. As you can see, this is a curvature. And it is a conventional typical cosmic ray event, It's completely different. It's different curvature. That's a typical time scale. On a level of 8 microsecond, you can see this from 0 to 8 microsecond. And in the cosmic rays, because it's very, very ultra relativistic, it's completely different story. This much larger area is covered much shorter period of time. Another one, absolutely unbelievably different so-called H. It is a H puzzle. So burst event, it looks like that. It is very white. While in the cosmic ray events, it's a pulse, very, very, very actually peaked because of relativistic particle. Now, it was some kind of journalist published a story about my paper about telescope array, but I better actually show a few slides the way how it can be resolved within the same scenario I discussed by myself. So in terms of AQNs annihilation, what's happening when AQNs or axion quark nuggets propagate in atmosphere, they experience a large number of annihilation. As I said, there are matter or there are antimatter nuggets. And internal temperature could be large, 10 keV or even larger. If this nugget appears somewhere under thunderstorm, in this case, in case of anti-nuggets, it would be so-called electrosphere. Like in atoms, you have electrons surrounding the proton. Here, the positrons surrounding antimatter nuggets. And in this case, they can be ionized. And they can be ionized because there is a known electric field does exist in thunderstorm on the level of kilovolt centimeter. It's known to exist. And this such kind of strong field is known to exist because people discussed thunderstorms as thunder flashes and lightning for many, many years. And the way how people normally consider that, there is a so-called avalanche scale. So it must be correlated on a relatively large scale, about 100 meters, such kind of electric field. And if nuggets appear in the such kind of background, in this case, it can be actually develop huge velocity and energy up to 10 MeV. And in this case, the mean free path is very large, and it can actually positrons with the 10 MeV. You can compute it easily. Mean free path is large, few kilometer scale, and it can definitely reach telescope array detector. So let me show what is actually spread in this case. So there is some kind of angle between different positrons which can exit electric field in the thunderstorm. And this spread is related to the typical velocity of positrons in the axion quark nuggets. And in this case, you can easily compute, it's just geometry. How long does it take actually to propagate along this path, and what is the typical distribution here, typical spread here. And it is a conventional geometry which tells you the following. If you take conventional, again, temperature and size distribution and all this stuff from nuggets, what we know.
You have 10 minutes, Ariel, 10 minutes
Okay.
to go.
Okay, good. Okay, I am about to finish that. So in this case, indeed, delta T time scale and delta S varies in the appropriate window, and this is a resolving of the curvature puzzle. So again, let me show the same plot. It is a curvature puzzle. So it's about 8 milliseconds, and this is about few kilometers. Very different from the conventional cosmic rays. Again, about thunderstorm. It is hard to understand how cosmic rays may know about the thunderstorm. And essentially, in this framework, it's easy to understand because essentially, once it enters the thunderstorm area, it produces such kind of positrons which can travel to telescope array. And clustering puzzle again can be resolved in a similar way because it is not one single pulse. It is a many pulses, because as long as nuggets propagates in this area, which is a very large, in this case, it produces such kind of pulses. Again, about H puzzle, let me show again this picture again. So instead of conventional cosmic ray pulse here, you have very broad distribution, because it's just the same positrons with approximately the same velocities, and they produce a broad H. Now, I want to, the next couple of minutes, I want to show completely different anomalous event, which again has been recently observed by ANITA, Antarctic Impulsive Transient Antenna. So what they observe so-called non-inverted polarity. So I'll show in a second. What is the problem with this event? The problem with this event is the following, that they observed such that it looks like that's Earth, that's a radius, and that's ANITA detector instrument right here. They observe some event when actually travels through the Earth. How do they know? Because they measure the angles. And if it is a conventional standard model neutrino, it must be traveling huge distance, almost size of Earth. And in this case, essentially, energy, we know that it must be huge. And it is actually completely excluded. So that's exactly the problem. And they observe such kind of events. Let me show precisely what they observed. So it is a non-inverted polarity. What they see, it is a non-inverted polarity. They definitely see such kind of non-inverted polarity, but all events they observe with non-inverted polarity, with a small angle, this one and this one, small angle. Why? Because, for example, if you have almost a little bit below horizon, and this is a distance about 35 kilometers, you will see that. But the conventional cosmic rays, they produce a conventional inverted polarity due to the reflection. So they observe two events like that, and it is very hard to explain. So again, it was a journalist description of the problem, and this is ANITA. It looks like that. And it definitely must be some kind of new physics involved. What is the new physics? The way how I want to explain that. So the way how I want to explain that, essentially, again, when nuggets travel through the interior, the temperature is much higher. You remember I discussed about 10 keV or 20 keV when it is an atmosphere. Now it's actually much denser traveling. And once temperature is so large, in this case, E plus and minus production becomes possible because the suppression factor is not huge. And because of that, nuggets could be ionized, and it is an ionization with a charge minus, because the positrons, when they leave, it is a charge minus. And this electron positrons will be experience attraction, so they go back to the nuggets, but electrons can be actually traveling outside because of the repulsion, and can reach the high energy on the level of 10 MeV again. So precisely the bunch of electrons emitted at the same instant from the same location at a very high energy produce a coherent radio pulse, and this radio pulse can be computed in the background of the geomagnetic B field, which is known to exist on Earth on the level 0.5 Gauss. And the number of electrons which actually can be emitted, it's about 10 to 8 to 10 to 9 can be estimated, and it is very similar to the cosmic rays with a huge energy, which indeed had been estimated by ANITA. So the signal's intensity would be very similar to the cosmic rays, which is indeed has been observed like that. Electric field can be, again, a distance r can be easily computed. You take the Landau textbook or Jackson textbook and you do the computations. So, and it is known what's happening with emission in this case. So again, all parameters such that cutoff frequency or typical duration or typical intensity of the pulse are very, very close to actually what has been observed by Anita. So, and it is already computations, and it should be compared with pulse which had been measured by Anita. All parameters are very, very similar. Now, I'm about to conclude because essentially out of time. So my conclusion is the following, that all people discuss a non-baryonic dark matter. It could be ordinary baryonic matter we know and love, which is actually in the exotic superconducting phase. Again, people discuss superconducting phase for many, many years, just in application of neutron stars. And we call this model axion quark nugget. A ratio between dark and visible, which is a very hard to understand in Wimp's ideology paradigm. It's very generic consequence of this framework, because it is everything is proportional one and the same fundamental scale. So this model offers simultaneous resolution of many, many problems. I'll show a slide in a second. Today I discuss mostly square quakes and telescope array and Anita. Now, let me show the just almost last slide that I discuss only 3 elements: Anita, telescope array, and skyquakes. But there are many, many other problems which had been discussed here, and the axion field plays a key role here. And essentially, CAST-CAP experiment at CERN now actually trying to see so-called daily modulations of these axions. And I have no time to discuss that. Okay, now I want to show the picture which I observed from Dima Butler talk, probably in Korea, or it was somewhere else. So essentially the way how he wanted to present the problem that there is a matter-antimatter asymmetries, there is a similarity between matter-dark matter, there is a dark energy. He had many, many different elephants in the same room. The way how I see a problem, it's completely different. So we have one and the same elephant, but different people from different fields conducting different experiments around the globe, and they observe and study different parts of the same body of the same elephant. So let me conclude here. Thank you.
Thank you very much, Ariel, for the very nice talk. So we have time for one quick question. If you have a question, please use either the reaction tab or use the chat function. Sebastian, please.
Yeah, I have one question. Maybe you can talk a little bit about the lithium problem and how you tackle this question.
So again, about what problem?
The lithium.
Oh, about the lithium problem.
Yeah.
Sorry, I didn't mention that, but it is definitely way. We wrote a paper with Vita Flambaum here. So because it's already published and it is a relatively old, the idea is the following, that during the Big Bang nucleosynthesis, when you have positrons in these nuggets, at this temperature, you can actually observe the following. Again, you have ionization, but what is important that essentially you have the charge of these nuggets would be negative just because of the ionization of the positrons. So what's happening is the following, that the proton and all other ions will be attracted because of this negative charge. But you remember that there is actually attraction is proportional to the charge. So when Z is 1, for example, proton, or Z equals 2 helium, it's not sufficiently strong attraction. So you just, everything goes precisely what people discuss in a conventional Big Bang nucleosynthesis. But for Z equals 3 and larger, what we computed this exponent, we computed this interaction, it was sufficiently strong such that some of the lithium ions, will be attracted and will stay with the nuggets forever because of the attraction for a long, long period of time. So it means that they will be eventually annihilated with anti-nuggets, will be annihilated, so they are lost for observation. And this is a very natural and very simple explanation for the lithium puzzle, which again, one of the very famous puzzles in our community, because people don't know how to resolve that in a conventional way. But here again, without a single fitting parameter, all parameters are the same which had been used before, you definitely see that order of 1 effect. So order of 1 means that large portion of lithium ions will be lost in annihilation with nuggets. That's main idea.
Okay, sounds interesting. Thanks.
So, thank you very much to Ariel. And
Okay.
without further ado, I'd like to introduce the next speaker, Jihan Ye. If you could please share your slides.
Yes. Can you see it?
Yes, I can see your slides. And
I need to go to full screen. Is it full screen?
and it's full screen now.
So,
It's in a, yeah, oh, perfect.
okay.
Whenever you're ready.
Yeah, thank you. First of all, I would like to thank the organization for organizing this session. And my name is Jihan Ye from the group of Tayam Stoiber at the Quest Institute. So together with our colleagues, we focus on a test of local Lorentz invariance with ytterbium-172 ion Coulomb crystals. And from now on, local Lorentz invariance, I'll just use LLI in short. This is a quick content. So I will first give a quick introduction into why we want to test the LLI and an overview of previous experiments. Then the detection scheme of how we want to do this, together with the experimental setup and the preparations that we have done so far for a single ion or a multi-ion LLI test. And last but not least, then the conclusion. First introduction. So probably we're all very familiar now that physicists believe that there is a theory that could unify all the forces. However, it has not been so successful yet when it comes to quantum mechanics and the general theory of relativity. So one of the ways to look at this is to look at the basic assumptions of these theories. For example, the Einstein's equivalence principle, which is the basis of the general theory of relativity. It consists of the universality of free fall, local position invariance, and local Lorentz invariance. And of our particular interest, we look at the local Lorentz invariance. One of the frameworks that discuss the evaluation of the local Lorentz invariance is the standard model extension. It quantifies the hypothetical Lorentz violation by adding a symmetry breaking tensor to the kinetic term of the standard model Lagrangian. So from the derivation, it leads to that a small shift of energy level comes from this violation in the bound electron state. And here's the equation of this energy shift. The first term here are some constants once you have decided which atom you want to use. And the second term here is the term that we're more interested in, which consists of the second order elements of the symmetry breaking tensor that characterizes the Lorentz violation and the components of the quadruple momentum operator of the electron momentum distribution together with the electron mass. So one of the ways to test this is something similar to a Michelson-Morley experiment. So a quick recap into this experiment. What they did was they have a laser interferometer with 2 orthogonally oriented laser arms, and this interferometer was placed on a rotating platform. And as the platform rotates, they try to measure the isotropy of the speed of light. So what one can do is very similar, but instead of using the bulk laser arms, we can use two orthogonally oriented electron orbitals and see if this potential Lorentz violation have an effect on these two electron orbitals. The first measurement of the LLI to be done in the electron photon sector was by the group of Harman Hefner, where they used entangled calcium ions. Then in 2016, Vladimir Chuba proposed to use ytterbium due to the F shell being much more localized compared to the D shell in calcium, and it also having a much stronger electron momentum. With that, you gain around a magnitude more sensitivity to the Lorentz violation signal with ytterbium. So making use of this higher sensitivity, in 2019, an experiment was done, which is led by the group of Niels Huntermann and Eka Pike, where they measured the absolute frequency difference of two ion clocks that are orthogonally oriented. And from their measurements, they deduced that one of the components of this symmetry breaking tensor has an upper bound of 8.1 times 10 to the minus 21. So what we will do is somewhat similar. We will also use ytterbium because of the very highly forbidden octuple transition and the long living F state. And our experiment consists of 3 parts. First is the excitation from the ground state to the F state, and then a sequence of composite RF pulse sequence that rotates the spin within the F state such that the population goes into different states that have different electron orbits, and they're almost orthogonal to each other. And then we bring them back into the same state, and we measure the population deviation with the de-excitation back to the S state. So as the experiment rotates around the sun, if the Lorentz violation exists, then we should see a signal that has a fluctuation or a deviation at the time scale of a day or half a day. The advantage of this method is that we have more common, most systematic effects because we're only looking at a single system. And a bit more detail into the composite RF pulse sequence. If you look at the picture here, the RF pulse sequence consists of 3 main parts. The first part and the third part are half Ramsey half pi pulses, which first is to spread the population into different Zeeman substates, and the last one is to bring them back into the initial state. And the middle part, or the second part of it, is a spin echo like sequence that rotates the state vectors on the equator of the Bloch-sphere such that we can suppress the magnetic field noise. And with this method, we deduce that we have the ability to measure the components of the Lorentz validation tensor with a sensitivity of 3.11 times 10 to the minus 18 divided by square root of nt tau, where the small n is the number of ions that will be in the experiment. Tau is the Ramsey dark time, where the Lorentz violation signal will be accumulated, and t is the total measurement time. The advantage of this composite RF pulse sequence is that we can make use of the long coherence time in the RF regime, which is about 1.5 seconds, and the measurement will be shown later on. And with that and a single ion, we only need 2 days of averaging time to improve the current best bounds, theoretically. And also, we have this scalability to multiple ions from this equation here. And now it comes to the experimental setup. So as previously mentioned, there are 3 main parts: the excitation to the F state with the highly forbidden electric octopole transition, and then the composite RF pulse sequence and the de-excitation. So for the first and the third part, we need very stable laser and a very stable magnetic field background. And for the laser part, we're very lucky that we have the PTB infrastructure and the collaboration with the ytterbium-171 ion clock group. From the clock group, we received their 934 nanometer laser light, which is referenced to their 171 ytterbium ion and also referenced to the silicon cavity at PTB. we get the light from then, and then with two laser setups, we amplify the laser power and a gigahertz AOM to bridge the isotope shift. And this light is then sent to the SSG for frequency doubling, then goes to the ion. From this, we were able to receive the laser light that is at sub-Hertz stability. And as for the magnetic field part, we need feedback stabilization because we're using a even isotope, and from this these three-dimensional coils, we were able to reduce the incoherent noise to below 5 nanotesla with it and a B field sensor that is close to the ion. And due to the fact that the octopole excitation takes more than 20 milliseconds, the noise from the 50 hertz and harmonics from main power lines kicks in, and this will perturb the transitions. And to map out the noise of the 50 hertz and harmonics, we make use of the quadrupole transition, the 411 nanometer quadrupole transition in the ytterbium-172 ion. And we continuously measure the carrier, the center frequency of it with respect to the line trigger. So what you see from the picture, from the measurement graph here, the y-axis is the deviation of the center frequency with respect to the mean of it, with the x-axis being the time difference between the center frequency measurement and the line trigger. As you can see, the red curve is the one when the feed forward is not on, and the black curve is when it's on. And with the feed forward stabilization, we were able to reduce coherent noise from 70 nanotesla by a factor of 10 to about 7 nanotesla. With these two matters set, we were able and successfully to excite the electric octopole transition in ytterbium-172 in 2019. And this is the picture. So with around 265 milliseconds of pulse duration, we were able to measure a full width half maximum line width of 6 hertz. And we were also able to reproducibly and nicely excite the ion with around 42 milliseconds of pulse duration to 90% excitation. And so now we can excite it to the F state. So the next part is the composite RF pulse sequence. To test the composite RF pulse sequence, we first tested it in the ground state, which is a simple state that consists of only two states, namely the S-1/2 state and the S+1/2 state. The way to do it, we did it, is to first initialize the state in the S-1/2 state, and then apply this composite RF pulse sequence. So if the composite RF pulse sequence can suppress the magnetic field noise, then the population in the S-1/2 state should stay the same. And here's the measurement that we did. So the way that we detect it is by using the quadrupole transition, and that's why you see there's roughly 90% excitation. And the graph is the excitation versus the Ramsey dark time. So you can see from the measurement that we have a long coherence time in the RF region up to 1.5 seconds. And with a 3-hour long measurement where we kept the Ramsey dark time to about 1 second, we see that the measurement was very stable. So with this, we are in principle ready for a single LLI test, which we will do very soon. Next is the preparation for multiple ions. Our ultimate goal is to test the LLI with multiple ions, because we can see from earlier that the sensitivity scales with the square root of the number of ions in the experiment. So for example, if we scale it up to 10 ions, we gain another factor of square root of 10. Our group has expertise at multi-ion precision measurements, and we also develop and manufacture good traps with very low heating rate, which are ideal for multi-ion clocks and other multi-ion precision measurements like the LLI test. Then the next question when we want to do a multi-LLI test is how we want to excite them. So for a single ion, it's pretty simple. We just need to focus it down to one ion and then it's it. But for multiple ions, it's more complicated. Geometrically, it is easier if you excite it along the trap axis, or we call it the axial direction. and it would be a bit more harder if we want to do it radially, because we would need to create a flat top head beam. And the reason why we want to discuss which method to take is because after the this RF pulse, composite RF pulse sequence that takes about 1 to 1.5 seconds, the ion heats up. So the thermal decoherence kicks in, and then the excitation becomes very unreliable. And we want to see how unreliable this is. So we assumed that we have 10 ions in the experiment and a very tight confinement in the radial direction of about 1 megahertz of secular frequency and about 150 kilohertz in the axial direction. And we did some simulation with both Doppler cooled case and the ground state cooled case. And for both cases, the radial direction seems to be okay. So this ratio here, the omega 0, this is the Rabi frequency of the initial excitation, and the omega here is the Rabi frequency of the de-excitation. For the radial direction, it differs by only about 2 to 3% for both Doppler cooled and ground state cooled. But for the axial direction, either cases works. It will give more than 20% of deviation, and so in conclusion, axial spectroscopy will not work. So we can only work with the radial direction with a flat top head beam. We now have a faceplate, and we tested it with the 411 nanometer laser on the camera as an initial test. And by taking the cross section of them and averaging, we see that there's about 2% of intensity fluctuation. But we're not sure how the ion sees it, so we will soon test this on the ion to see if this is enough. And then to the conclusion part. So I've shown that we can reproducibly and to excite the F state to 90%. And we also have the long coherence time in the RF regime with the test in the ground state and the long stability of this RF pulse sequence. So we are in principle ready for a single ion LLI test, which we will do in a few months. And we have a good trap that can easily scale the number of ions to 10 or even 30. And once we test that the beam profile shaping is successful, we will be doing the multi-ion LLI test. With that, I would like to thank you for your attention with the lovely group picture of ours at the Quarks Institute at Quest. And thank you for your attention.
Oh, so thank you very much for the nice talk. You actually have quite a lot of time to go. If there's anything else that you'd like to discuss, maybe.
So I have a question regarding actually for the isotope shift measurement, that because we have now the ability with the collaboration with the clock group, we can also measure quadrupole and octopole transitions of different even isotopes. And I was wondering if this can give a big contribution to the isotope shift measurement.
Maybe one of our
maybe
participants might be able to answer.
That's me, I guess. Can you guys see me? Well, maybe because my camera is on. I think this would be great if can you guys hear me?
Yeah.
Okay, I think that would be great. If I saw your you measure one ion with or one isotope with 6 hertz, right? I mean,
yes.
The line with 6 hertz, so then you can go well below 1 hertz, right?
Well,
so,
we are now currently limited by the magnetic field noise, but
okay.
In principle, if we for example, have a mu mantle shield that can really cover up the environment, and we can measure to subhertz.
Okay, so I think this would be great if you could do this for a chain of, well, at least 5 isotopes, if that's possible. And you trap them, right? So once you trap it, you measure it, right? It doesn't go away, right? So you don't suffer by having low abundance for some isotopes, right?
Yeah.
So I think that would be great. Yes, that would definitely contribute. Yeah. And since I am on, can I also ask you? At some point my connection broke, so I'm not sure if you spoke about this. But what's your projection for improving the existing constraints on LLI? It's like a factor of 10 or?
So this, I can go to this slide here. So the reason why we can improve this from averaging, so for the measurement of the clock comparison, it was 45 days. And for us, it's 2, and theoretically it's 2. And the reason is because we use the coherence time in the RF regime that is 1.5 seconds, while in the clock measurement, they were using 400 milliseconds of excitation. And also we gained a lot by including more ions into the measurement. And another is the so from just only also for theoretical calculation, the state or the transition that the clock group was using was the the SMF equals 0 to FMF equals to 0. So in principle, they're actually not using the very full potential of the ytterbium. They were using mainly I think the 1/2 states, the sensitivity of the 1/2 state, but we are like about 2.4% more sensitive because we're also using the 7/2 state. So with this, overall, we gain a bit more sensitivity, and we need less averaging time then. And
okay.
yeah, then like how much we can gain depends on how many ions we use and how long we do the measurement.
Okay, but the stability of the machine is good. You can run it for many days, let's say, without issues. Okay.
Yeah.
That's great. Okay, thanks.
Any other questions? So if you have a question, either through the reactions tab or the chat tab. So it was a very clear talk then. Well, if we don't have any questions, let's thank Chihan, and our next speaker is Sophia Crawford.
Hi everyone. Let me just share my screen. Just one second.
Oh, perfect. Whenever you're ready.
Okay, thank you so much. So hi everyone, thank you so much for coming today. My name is Sophia Crawford. I am a research fellow at University College London, and today I'm going to talk to you about constraining modified gravity with quantum optomechanics. This is joint work together with Dennis Rätzel, who's at Free University Berlin, and with Steven Stupira at University College London. So thank you so much to the organizers for allowing us to speak about this topic, and let's get right into it. So this is a quick outline of the talk. So I'll first talk a bit about searches for modified gravity. I'll then introduce optomechanics and optomechanical sensing. I'll keep it quite broad because I think we have quite a broad audience here. I'll then briefly introduce the quantum metrology tools that we're using to investigate these matters. And finally, I'll introduce some results. So this is a theoretical study, and if you're interested, the paper containing these results should be appearing in on the archive within the next few weeks. Okay, so ever since general relativity was first proposed and introduced, there have been loads and loads of theories that propose ways to extend and go beyond the standard theories. And this can be in many different ways by adding additional degrees of freedom, additional scalar fields. Some of them are to specifically solve problems, but otherwise it also involves looking at how we can extend these theories and what is possible. One of the biggest challenges that we're trying to resolve in this way is to address the cosmological constant problem. This is the problem that the observed value of vacuum fluctuations and the predicted values for the calculation from quantum field theory is about 120 orders of magnitude apart. And the proposed solution to this is to change GR to allow the cosmological constant to be set to 0, and to instead introduce or allow these observed vacuum fluctuations to come from other effects. And there are many, many different ways to do so, but one of the main ones is that also encompasses many of these changes is to change the Newtonian potential by adding a Yukawa-like modification to it. And many of the proposed theories can be mapped onto these changes. So here we have added an additional term here where alpha is the strength of the term and lambda is the range of the modification. Now, but the challenge is with searching for modified gravity is that these parameter ranges have been already very much constrained from tests of solar system-wide tests to laboratory tests. So here you can see two graphs from this paper here, review short-range gravity experiments in the LHC era. And as you can see, a large range of these parameters, lambda and alpha here, have already been constrained. And the main challenge involves going to smaller ranges where lambda here is smaller, which involves laboratory precision experiments where you have to get very, very close to the gravitating object to be able to see these effects. And this is where quantum experiments can have a striking advantage in the sense that we can use the small scale of experiments in addition to properties such as coherence and entanglement to fundamentally increase the sensitivity of the system. And indeed, many searches have been proposed with quantum experiments. For example, cold atom interferometry, which I'll talk about in a minute, is one of the leading candidates for pushing these bounds or further constraining these bounds. But also what I'll talk about today, quantum optomechanics, is a potential platform where these effects could be useful to push the sensitivity. Okay. So a particular model which explains, which is one of the leading candidates for dark energy, and which also explains perhaps why some of these effects that we haven't seen in the laboratory could instead be affecting the large space or parameter ranges on large spaces, is the chameleon field. So the chameleon field is screened by local matter, and this explains why in current experiments we might not have been able to see it, simply because local matter density is quite high. For example, even in vacuum chambers, even if you have a decent vacuum, it can still screen out much of this effect. And that means it's generally quite difficult to detect in the laboratory. And I've tried to depict it here with a source that when a test particle here comes very close to the source is screened by the chameleon field here, but the effect of the modification of the chameleon field can be detected beyond this screening range. And the potential of the chameleon field is shown here, where here lambda is the energy scale of the chameleon field and m is the coupling to gravity. So this is one of the main candidates together with just Yukawa-like modifications that we'll examine in this work. And the main question we want to examine is how can we use optomechanical systems to constrain these theories? And the three parameters, as I said, in this case is lambda and big M. So as I mentioned before, one of the leading candidates for doing so is to use cold atoms and use either a free flight system or a cold atom fountain to constrain, to detect, to very finely probe gravity, and thereby trying to detect deviations from Newtonian gravity, which in turn allows us to constrain these proposed theories further. So in this experiment here by Hamilton et al., you have a large aluminium sphere and you suspend it in a cavity, and you have a tiny cloud of cesium atoms suspended very close to this sphere. And the sphere is moved back and forth, and this cloud of atoms here, they are so contained in the close to this object, and the modified gravity effect is deduced by looking at the phase shift introduced by the effect. And you have to keep the vacuum very high in order to detect these chameleon theories, but that is possible. And due to the nice property of the atoms, which is that they are all the same, and they're really easy to control, this is definitely a really strong contender for pushing the constraints. And current experiments at Imperial College are trying to push this even further. So in our case, we're interested in looking at whether other quantum platforms, other experimental platforms, can be used in a similar manner to further constrain these theories. And one of them is so-called optomechanical systems. So here, similarly to the atomic case, we have light interacting with some mechanical element, but in this case, we don't have atoms, but we rather have, well, we have systems made up of many, many atoms. So for example, some examples of optomechanical systems include suspended membranes, we have tight small mirrors here, we have drums and even levitated nanospheres. So what's really exciting lately is that some of these experiments, especially these with the levitated nanospheres performed in Vienna, they have reached ground state cooling, which means that you can start probing the quantum regime for these systems. And there are many different platforms for these optomechanical experiments. You could also have superfluid experiments starting to approach this regime. But what's good for us is that they are all described with very similar mathematical language. And so in this work, we take on a very general description of these systems, which will vary a little bit for each system, but the broad mathematics is the same that describes the dynamics. And what we are aiming to do here is to look at how, in the most ideal case, what limits can be placed on modified gravity theories. So to describe the evolution of the system, we use the standard optomechanical Hamiltonian. So here we have the free evolution of the optics and we have the free evolution of the mechanics. So we choose a single mechanical mode in one direction. And then we have the interaction term, which can be derived in many different ways, but often is approximated until you get essentially to this form here. So we have a K, which is the coupling strength between light and matter. I believe an H bar is missing here, apologies for that. And this K essentially couples the photon pressure to the center of mass position of the mechanical element. And this is often derived by looking, for example, at small perturbations of a moving mirror. That's perhaps the easiest derivation. And then adding the laser light and looking at how much the mirror is perturbed, and then considering the change of the length of the cavity to drive this Hamiltonian. And here you notice that I made this K time dependent. That can happen in some systems very naturally, that you have a micro motion that modulates this coupling in time. In our case, we are interested in adding this modulation because we know from previous results that it can help us fundamentally improve the sensitivity of the system. So I'll return to this later. Okay, so in our case, what we're envisioning here is a very similar setup to the atom interferometry experiment, but where we have a vacuum chamber that contains some source mass, in this case made of gold, that oscillates. It's oscillated by perhaps a piezo or similar, where you have a small oscillation amplitude epsilon, and here next to it you place your optomechanical system, which here in this case I've modeled as a moving mirror, and the distance, the separation of the two systems is given by R0. So this is the setup that we have in mind. So let's briefly look at how we can model the effect that arises from this moving sphere, the source sphere, onto the optomechanical system. So in our case, we start with a gravitational potential, but because we know that gravity is very weak, we can linearize it and then model this linear contribution to it as a perturbation of as a contribution to the optomechanical dynamics. So we take the full gravitational potential, we Taylor expand it around R0, and then as long as this perturbation is small enough, we can promote it to an operator, and which ultimately the Hamiltonian that we obtain becomes the following. So here we have the gradient of the potential, gravitational potential, times the 0-point fluctuation, and this B dagger plus B, which is the center of mass contribution perturbation of the mechanical element. So to further derive some linear, some analytic results to our setting. We want to model the movement of the source mass. So previously I left it general, but if we now assume that it's some sinusoidal motion that oscillates around some r distance r naught, we're able to linearize the potential further if we assume that this oscillation amplitude is very small. So if we let this epsilon be very small, then we can write the full gravitational potential as this here. So this is the contribution from the Newtonian gravitational potential. And then we have this additional term here, which arises from the modified gravitational potential contribution. And here I've kept the Yukawa parameterization of alpha and lambda, but you could of course also map any of take your favorite modified gravity theory and also map it to these parameters here. So here I've defined two parameters, kappa and sigma, which basically describe a constant contribution to this potential and a time-dependent contribution. So sigma here is multiplied by this cosine omega t, and we make this distinction because in an actual experiment, it would probably be quite difficult to see kappa in the sense that it is a static contribution. And to actually see a change in your dynamics due to kappa, you would have to physically move or increase the separation between the two systems, because as you can see here, it depends on R naught. And we anticipate this to be quite difficult to actually see compared to a static noise floor or to any noise floor. So instead, what you could do is to take your data and then Fourier transform it to obtain this signal here, which we think should be much more distinct compared with any noise in the system. So in subsequent presentation of the results, I will focus on this contribution sigma. Okay, so another thing that we did in our investigation here is to consider the fact that the optomechanical system is quite large compared with, for example, an atom. So in many of the previous investigations into the sensitivity that can be achieved with similar systems, an approximation was made that the probe itself here is a point particle. Now, that is not always possible with the optomechanical system because it is quite large. They are among the largest quantum systems that we can control in the laboratory. So therefore, what we had to do is to also consider the screening that comes from the probe. So in this setting, what we have done here is we assumed a spherical optomechanical system. So this description does not apply to all different experimental platforms, but rather applies mainly to levitated optomechanical systems, which can come in the shape of spheres. And we took both the screening of the source sphere into account, but also the reaction or the response of the probe, given that it's not a point particle. And I'll present those results in a bit. Okay, so in order to derive the fundamental sensitivity of the system to these modifications, we use what is known as the quantum Fisher information. So this is a theoretical tool that quantifies the change over quantum states with respect to some external parameter. So in this case, theta. So if theta is our, say, the contribution to the potential due to modified gravity, either as kappa or sigma, in our case, we prefer sigma because it's time dependent. Then we can relate the variance of theta that can be obtained through an experiment to the Fisher information through the Kramer-Rao bound. So here we have the number of measurements, this M, and we have this IF is the quantum Fisher information. And as you can see, if you had the ability to perform as many measurements as you want, you can reduce the variance here, but the Fisher information will tell you how quickly you can get there. And so our objective is always to maximize the quantum Fisher information, which tells you essentially how much information you gain from a single measurement on your system. What we should mention though is that the quantum Fisher information is the optimal bound, so the ultimate, the optimization over all possible measurements. And so the additional work would be required to see in a laboratory setting, when you perform a measurement, what sensitivity you will actually get. And the results that follow now they're much based on previous work. So first gravimetry of constant signals, and then we developed some metrology tools for time-dependent signals. And finally, we also considered just detecting Newtonian gravity with tabletop experiments of the mechanical systems. And I should emphasize that these calculations are all for nonlinear optomechanics, while often in experiments the interaction is linearized, but we anticipate the nonlinear description to be more fundamental and also capture some of the sensitivity of the linearized version. Okay, so let's proceed to some of the results. So here we have the ability, so using the quantum Fisher information and these linearizations we did before, we are able to derive the following expressions for the sensitivity of measuring this kappa and sigma. So here again, m is the number of measurements we have, and gn is the Newtonian acceleration, essentially, gravitational acceleration, and here delta n a is the standard deviation of the photon number, or the square root of the photon number with variance. We also here have the mechanical frequency of the mechanical elements. And as you can see, the scaling is quite unfavorable with omega m to the fifth. Here I have the mass of the optomechanical probe and the coupling, K naught is the coupling, E epsilon was the oscillation amplitude. And then finally, we have this N here, which arises because we're letting the system evolve for 2 pi n, and we assume that the measurement happens at this time. So these results are for when the optomechanical coupling is constant. So it's just a constant life-matter coupling, but we can now proceed to also assume that this coupling varies with time. So when it varies sinusoidally and also at resonance, so when we modulate the coupling at the same frequency as we shake the source sphere, we can instead derive these results. And the interesting thing here is that we get an n squared. So n is essentially time. And this means that we have a better scaling as a function of time when performing this experiment. And because it is a quantum experiment, it is likely that you will get a lot of decoherence effects. So it's in your favor to try and optimize the sensitivity in as short as time as possible. But I should also emphasize that these calculations are for a closed system, so do not include noise. So they will instead provide a fundamental bound on the sensitivity that you can get. Okay, so here are just a list of parameters that we assumed for our results. With these parameters, we try to stay as close as possible to the current state of the art in experiments. But also, if you were to change these parameters, you could improve or make worse the results that I will show you shortly. Something to point out is that we have assumed that you can achieve a very high vacuum, so very good quality of the vacuum in your chamber, which is a challenging thing to do, but current experiments are nearing these kind of numbers. And I believe that this density that we have assumed here is approximately equal to 10 to the minus 10 millibar. So here we also have assumed the optomechanical coupling to be quite weak. We've also, which is quite accurate of current experiments. We've also pushed the mechanical frequency to be quite low because we had an unfavorable scaling in the sensitivity with this. We should point out that this kind of frequency has been achieved in the levitated experiments. Furthermore, we also have quite a light probe mass, which is also more reminiscent of the levitated systems, but this could be also increased if one wished to model a different system. Finally, we've also assumed that you can squeeze the input.
10 minutes to go, Sophia.
Thank you so much. That should be enough. We've assumed that you can squeeze your light quite a lot, but this is also we're also getting there in terms of this has been achieved in a current experiment. Okay, so onto the results. So by plotting the quantum Fisher information and then dividing it by the strength of the effect, we've plotted these bounds where this ratio is less than 1. So assuming that the error of your measurement or the variance that you achieve in the end is smaller than the strength of the effect. So here we've plotted the bounds in terms of alpha and lambda. And some features of the plots include the fact that the dark purple shows you the result for a constant optomechanical coupling, whereas light purple includes the results for a modulated optomechanical coupling. So this is showing the sigma bounds, because that's what's the time-dependent effect that we think we can see much easier in an experiment. We've also included the results for kappa for constant detecting a constant contribution, but we don't think it's as significant. So here you can also see that modulating the optomechanical coupling significantly improves by about 1 order of magnitude the sensitivity that you get. Moving on to the chameleon bands. So here we have two different sets of dark purple and light purple bands. And we plotted them in terms of the coupling to gravity, in terms of the Planck mass, and the energy scale of the system, and or energy scale of the theory. And here the key features include the fact that the dark purple area includes the screening from the sphere, so from the probe, and this is for a spherical probe. So this is not valid for all optomechanical settings. If you had a non-spherical probe, you would probably be somewhere between these two bounds, where the best possible bound is for a point particle approximation. So maybe if you had a moving mirror, you'd expect to be somewhere in between. And the other features of this plot can be explained by looking at these two lines. So here the pink line shows where the screening from the source sphere starts to become important. So below this line, the screening is non-zero. And the orange line shows that the screening from the probe is also non-zero, which explains this dip here, or this bend in towards a less sensitive or a less favorable bound for the sensitivity. Okay, so we can proceed to compare these bounds, these predictions, with current experiments and experimentally excluded regions. So we see here on the left that in terms of alpha and lambda, our predictions don't actually do much better than the currently existing bounds. And this tells us that we probably have to improve the parameters that we put in for the optomechanical systems, and that if you use the parameters that we use, we might not be able to achieve much improvements on the constraints. And also remember this is the best possible. This is for closed system dynamics. So if you want to do better, you would have to deal with noise as well. So you likely would want to push these parameters much further before you can take that reduction from noise. However, for the chameleon parameters, we see that we could potentially with these systems push into especially smaller lambda with these systems. And we believe that the more favorable bounds here are due to the higher vacuum that we assumed in these calculations, although the mapping between these two bounds is a bit non-trivial. Okay, so that brings me to the end of the talk. So just to summarize, we've derived the fundamental limits for detecting modified gravity with an optomechanical sensor in the nonlinear regime. And basically we conclude that if you have a higher net vacuum, the optomechanical sensor could be used to potentially further constrain chameleon theories, which is really exciting. So with that, I'd like to thank my co-authors, Dennis Reitzel and Steven Stupera. And we hope that the paper containing these results will appear on the archive in the next few weeks. Thank you so much.
Thank you for the nice talk, Sophia. Are there any questions? I actually have a question.
Sure.
So in your work, you consider universal types of couplings. Would there be any sort of advantage if you were to consider either simple Yukawa forces or chameleon models with sort of non-universal couplings which induce equivalence principle violation?
Oh, that is a really good question. I have to say that I'm coming from the quantum sensing point of view, so I don't think I'm able to answer that question. But I think as long as you can map as long as you could model the effects of those couplings as a contribution to the dynamics of the Hamiltonian, then you could compare using these metrology tools. You could compare whether you could distinguish those additional effects for those couplings in this way. So sorry, I'm probably not able to give a better answer than that.
I mean, I think you probably can do it. You wouldn't see necessarily equivalence principle violation because you only have a single, say, material type in your experiment, but I think you can relate the couplings between your model and just a slightly different model, which has, say, maybe different couplings to the nucleons, to the electron, to the electromagnetic field.
Absolutely. I think if it comes down to, so for equivalence principle testing, you would already have a difference in the probes can be made of different material, and you could test it that way. Excuse me. And so that would be certainly possible. One thing I also wanted to mention is that we think that that could be a unique advantage also in the fact that your optomechanical system can be differently shaped. So we know that the spherical probes have the worst screening essentially, but if you could have, for example, an asymmetric source and an asymmetric probe, you could potentially increase the coupling between them.
Oh, thank you. Are there any other questions? Oh, Sebastian, please.
Hi, Sophia.
Hi.
I remember last time we talked about this, you were worried because of vacuum forces, like Casimir. Do you have to do some subtraction in your experiment?
Yes, yes, absolutely. So we were always, I didn't mention that in this talk, but we were always worried about Casimir forces, because when this picture is a good one for this, when you want to put your optomechanical probe very close to the source sphere, you have to take that into account, that at some point you might come to a distance which is very, sorry, excuse me, that's good. You can drink some water. You will always have Casimir effects that arise from this. So we think one way to deal with this could potentially be to add a shield between these two objects. So as long as you have then a moving source sphere, then the moving contribution, the sort of time-dependent contribution will be sort of distinguishable from the Casimir force, which would be constant. So we think that there are ways, there could be ways to mitigate these effects. How the additional screening, though, from such a field could affect from the shield could affect the possibility of detecting the chameleon field, for example, is something that would have to be investigated. So that could potentially be quite detrimental.
Great, thanks.
Thank you.
Will we have time for one final quick question? I don't see any raised hands. So in that case, let's thank Sophia. And our next speaker is Sebastian Franchino Viñas. Whenever you're ready.
Okay, so you see the screen, I think.
Yes, I can see the screen and
okay,
the
and
pointer and the annotations in green.
Super. So I would like to talk about the lithium problem and try to relate this to the Hubble tension. Let me first of all introduce the collaboration. It's pretty small, so it's me on the left. I'm a quantum field theorist, and so everything that you will hear today is from a quantum field theorist point of view. And on the right, you can see my collaborator, Mercedes Mosquera, from the University of La Plata in Argentina. She's an astrophysicist, and has devoted many years to the study of Big Bang nucleosynthesis. The outline would be the following. I will talk a little bit about BBN, Big Bang nucleosynthesis, for those of you who don't come from this background. Then I will talk about the variation of constants. I will talk about the basics of the H0 problem, the Hubble problem, and then I will state some conclusions. So let's have a look at this picture. So we think that there was a Big Bang at the beginning of the times. Then there was a period of inflation. The universe was growing very rapidly. At the same time, or at the end of inflation, you will have a reheating, and then the universe will expand, so it will become cooler with time. You will meet the electroweak phase transition at some point, and then you will also pass another transition where QCD starts to confine. So at that point, you may follow this blue arrow, and you will have just a soup of electrons, positrons, protons, neutrons, photons, and neutrinos, and that's all what we want to have in order to study Big Bang nucleosynthesis, and everything is in thermodynamic equilibrium. The interesting thing to Big Bang nucleosynthesis comes when we met the green arc. So we have more or less 1 megaelectron volt, a temperature of 1 megaelectron volt, and the problem, or better, the situation is that the neutron decay just proceeds in one direction. Before this temperature, you will have protons plus electrons combining into neutrons, but then after you have this temperature, you reach the delta mass effective for this reaction, so this will proceed only to the right. After this happens, well, you will meet another bunch of nuclear reactions. For example, you could have a neutron and plus a proton, and that would become a deuterium. Or you will have also reactions between deuteriums and protons and photons, and you will get helium, and so on and so forth. These equations or these nuclear reactions are almost 100, the ones that we want to study. And at some point, which comes about 10 minutes after the Big Bang, the abundances of these elements wouldn't change anymore. That's because you don't have any more neutrons available, and there is also an atomic gap, an atomic mass gap at number 8. A typical plot you will obtain is the one on the left, top left. So there you can see the abundance of deuterium as a function of time or temperature, if you want to. And you see that it increases with time. Then, in particular for deuterium, you have a peak, a maximum at some point, and then it will stabilize to a constant value. Usually, one would say that the only cosmological parameter relevant to this process is the number of baryons, omega. So, for example, if you consider that omega increases, if you go from the red to the orange curve in the picture, then you will see that the production of deuterium begins early in time. Why is it that? Just because if you have more baryons at early times, you will have more probability of having a neutron and a proton interacting. That's all. But however, there's the problem that all the nuclear reactions are linked. So if you increase the number of baryons, you arrive earlier at the maximum for deuterium, but then because deuterium will have more time to produce helium, you will end in a smaller value, for the abundance of deuterium. So from this qualitative behavior, you can see what we are talking about. In the standard computations, what you will see is something like the plot on the bottom and the right. People will consider the abundance of helium and the abundance of deuterium, and they will try to guess from fitting the best value, the best possible value of the baryon number to know which is actually the number of baryons. So in this picture, you can see on green, you see the numerical computations. On gray, you can see the observational bounds. The gray strips are the observational bounds. And you can see that they intersect in the region given by the green lines that I am depicting, but also on the red lines that curiously are those given by Planck collaboration. Planck collaboration can also obtain the number of baryons, but using data at CMB. So that's an interesting point, and that's what the cosmological standard model dictates, that the number of baryons won't fluctuate going from BBN to CMB. Having said so, what would happen with other abundances? Well, let's just review again. From helium, we have no problem. Observations are in yellow and computations are in blue. The same one could say about deuterium. But if you go to lithium, which is the other third main element produced in Big Bang nucleosynthesis, you obtain the plot on the bottom and right. And there you can see that there is a problem. You have many sigmas between computations and observations. How can we understand that? Well, the fact is that it's not so easy to see the evolution of lithium in time from Big Bang till the contemporary era. Let me just sketch for every element how it goes. For example, for deuterium, it is only destroyed. So the evolution is rather simple. You have to look at old galaxies and you will have a good approximation of what the abundance was. For helium, it becomes a little bit more involved because it can be produced. It is produced exactly because we can burn hydrogen or deuterium. But you can keep the track of metallicity. When helium is produced, well, it will also be burned later, and it will produce heavier elements. So if you keep track of these heavier elements, you will know how much helium was produced in stars, for example. Another possibility is also to look in the past at far enough galaxies. In the case of lithium, well, it is burned in many stars, but it can also survive in some others. And the fact is that it is also produced in hotter interiors and also by spallation in collisions of cosmic rays. On the left, you see the plot of the abundance of lithium as a function of iron. And you see what I was talking about, that maybe if we look far enough in the past also for the lithium, we may obtain an approximation of the abundance of lithium just after the end of VBN. This is usually called the spike plateau for the ones who know that. And again, you can see that the standard VBN computations are really far from the observations. Which is the solution to this problem? Well, no one knows, but they are usually put into three categories, one of three categories. You may either modify the astrophysics, and the exponent of these explanations is this paper from 2006 in Nature. They consider that it was a diffusion process, a depletion process of lithium going into the center of the stars. So in the end, if the lithium is going into the stars, we won't see it, And that's the reason why the computations don't fit with observations. Another possibility is to study the nuclear reactions which are involved in this process. For example, you may have a look at this paper from last year, in which they were using mutual information and considering several reactions involving lithium to say that no acceptable solutions were found. And the last one is to invoke beyond the standard physics model, beyond the standard model physics, sorry. And I would say that's the category in which we fall with variation of constant. What kind of solutions have people studied in the past? Well, for example, we can have a look at this paper by Koch and Nunez and collaborators. They were considering some grand unified theories, and therefore they were considering variations in the Higgs, in the Yukawa couplings age, also in the scale of QCD, which was related to alpha, to the fine structure constant, and they found no solution. If you have a look at the plot on the left, you can see why. If you want the green strips, which are the observations, to fit the lithium data, well, you should be in this region for the Yukawa coupling parameter, but then you will be out for the corresponding region for the deuterium. So that's a problem. In order to solve this problem, there was a proposal by Berengut, Flambaum, Dmitriev. There are a series of papers discussing this possibility, which is actually to vary the quark mass. And indeed, in this case, they find some possibilities, some possible solution, because there is some intersection between the allowed regions for lithium and for deuterium, but of course also for helium. The only thing that I want to let you notice is that the uncertainties from the observational values was rather high at that time. Let me now go to our current paper that you will soon see on archives, I think. Our proposal now is to, of course, use the observations gathered in the last decade, and we propose a variation of Newton's constant and the fine structure constant. The idea is to fit these values to give the best yields possible. What we find is that Newton's constant should vary around 17%, and the fine structure constant should vary at the order of the 2 or 3. And that's independent also on the fact that we may or not vary the Higgs vacuum expectation value. If you go to the table on the bottom of this page, of this slide, you will see that our fits are very good. I mean, we are just a couple of sigmas away from the observational mean values. And you may also notice that the uncertainties that we are talking about are 1 order of magnitude smaller than the one you have seen on the previous slides. The same you can say about helium, and more importantly, well, you can see that the lithium problem is rather solved. If this is true, you will obtain a lithium abundance of 2.09, while the observational value is 2.01. So they are just 1 sigma away from each other, while you can see that the standard computation gives a number that is 5 or 4 or even 6 sigmas away from the observational values. Having said so, the question is if there are any motivations for proposing a varying fine structure constant, and the answer is yes. You can have some cosmological motivations. For example, in this paper by Webb, King, Murphy, Flambaum, and other collaborators, they have found that there should be a spatial variation of the fine structure constant, so that it behaves like if it were a multiple in the sky. So there are regions in the sky where you can see variations to the positive, and there are other positions in the sky where you will see a negative variation of alpha. Another explanation or motivation is from quantum field theory. There you have to renormalize. There will be a running coupling constant, therefore. And you can see this plot from Chloe, the Chloe collaboration. There you can see the behavior of alpha as a function of the energy of the process. And you may see that it varies, it indeed varies. And moreover, if you look, the red points are the experimental data, the blue points, the light blue points are the theoretical prediction, and they match impressively. On the left, instead, you may have the predictions for the running of alpha, and you can see that in the region around 1 MeV, which is the region that we are interested in BBM, there is a resonance that is given by electrons and positrons. So the sign would be the same as the one we need, but the magnitude is smaller. For Newton's constant, well, I could motivate it from quantum field theory in curved spaces. We have made some computations with Shapiro and Sanuso in 2019. I won't talk about that because I think it's too technical. I prefer to say that there are some phenomenological approaches, for example, that from Solar and collaborators, in which they consider a cosmological constant and then a Newton's constant that varies with G. They become functions of, they vary with H, the Hubble constant. So they become a function of Hubble constant, and you can look for this constant of proportionality. Another possibility is to consider that the variation of Newton's constant come from matter, from extra additional relativistic degrees of freedom, and that's what you can see in equation 3. And actually, that will relate our problem to the H0 problem, to the Hubble problem. What are we talking about when we talk about the Hubble problem? Well, look at the plot on the right. There you can see on the top that if you want to determine H0 indirectly, for example, using CMB or using BAO or using also the standard BBN, you will get a value of 66, 67 kilometers over second over megaparsecs for H0. But instead, if you want to determine it directly, for example, from Cepheids or supernova or even from lensing, you will obtain a value that is around 73, 74 in the same units. And moreover, there you can see that there are many sigmas given mainly by the precision of CMB determinations. I mean, between those measurements that are indirect and those measurements that are direct. Having said so, can we translate our variation in Newton's constant to a variation in H0? Yes, we can. We have to look at Friedman equation, and we consider two different universes. One has NF, the number of effective relativistic species that is given by 3, and the other one has an arbitrary number of effective degrees of freedom. A subtlety is that we want them to have the same product that is given by the horizon product times the H0 in order to avoid disagreements with observations, which are given mainly by baryonic acoustic oscillations. And then we obtain the following formula. Our Gedanken H0 with NF number of degrees of freedom will be proportional to that, which only 3.
Oh, Sebastian, you have 10 minutes to go, 10 minutes.
Okay, super. So there is a proportionality between them. and the proportionality is given exactly by the square root of some function of nf. So there you can see that if we consider our delta nf of order 1, we will effectively increase the result given by Planck, by the Planck collaboration, so that we may arrive, or we may just diminish the distance between these two measurements. In order to quantify what I have said, look at the plot on the bottom and right of your screen, and there you will see the probability distribution function of H0. In red, you see our results by using variation of constants at BBN, and in gray, you will see the results by using Cepheids and supernova by Ruiz et al. So the gray results are those from latent measurements, so direct measurements, and you can see that they agree, they pretty agree. So this could provide a solution to the H0 problem. Lastly, let me mention some other approaches. I have told you that Sola et al. Were using the phenomenological approach by these running vacuum models. In this paper, particularly, they have employed, or they have fitted CMB data, and they have also considered all the cosmological parameters that are considered usually in Planck, and they found that they could also solve the H0 problem by varying delta G on the order of 10%. So that would pretty much agree with our conclusion. There are also other possibilities to study, for example, grander unified theories at BBN, and you will probably hear something about this paper tomorrow, I think in the talk by Martins, so I won't explain a lot about that. And the next question that you could ask, well, what has been said by Planck in the last paper by them? They have seen that n effective should be at the order of 3 plus minus 0.5, let's say at 2 sigmas. So if you want to go further, you may do that, but the fact is that you will get a worse fit to sigma 8. Sigma 8 is a parameter that dictates the behavior of the power matter spectrum. So in this sense, we will have to explain how can we at the same time introduce this additional degree of freedom at BBN and then have no effect on the sigma 8, for example, at CMB. Okay, let me then state my conclusions. So we have revisited the lithium problem using the measurements from the last decade. Our proposal was to perform a variation of alpha, the fine structure constant, and of Gn, the Newton's constant, maybe also the Higgs vacuum expectation value, in order to provide a solution. The question if this is well motivated or not is still open. We have seen that for the delta alpha, the sign was okay if we trust the running coupling constant paradigm. But if that's the only way of explaining this, we will be an order of magnitude smaller in the predictions than in the actual computations that we have performed. We may also consider runnings in each single reaction. Remember that there is 100 of reactions, of nuclear reactions that are involved in Big Bang nucleosynthesis. So at this point, you may wonder whether there are some uncertainties on them, and yes, they are. There are some uncertainties. They weren't considered usually because people have tried to solve the whole lithium problem with these small uncertainties of the percent order, and that's not possible. Instead, in our proposal, well, an uncertainty on the 10% level would be much that what we wanted actually. Regarding Newton's constant, I can say that the interpretation in terms of the effective number of relativistic species is promising. It gives a number of 1 of increased number, and it could be related to the H0 problem. So in this paradigm, lithium could be employed as a Hubble meter, as a parameter that could determine the actual value of H0. Another possibility is to link these results with the serial neutrino. As you may know, from the anomalies that were detected in Mini-Boon or in LSND, they have solved these anomalies by introducing exactly 1 additional neutrino. So maybe it could be the case that our additional relativistic species could be that serial neutrino. And in the end, well, we have to think about how to avoid the sigma 8 constraints on the matter power spectrum that I was talking about. And one possibility could be to study interaction, but it is still uncertain. So many thanks, and please ask me.
Thank you very much for the talk. Are there any questions?
Yeah,
Ariel, please.
Oh, sorry.
Okay, so I have a couple of questions, and let me start with your slide with equation 2.
Yeah, sure. Here we are.
Okay, so essentially, what you say the following: that the right-hand side is must be proportional to h square or h dot. And it is definitely correct result because the curvature is proportional to h square or h dot, and that's exactly the conventional way. My question is the following: that let's assume that you have term proportional to h, linear part of h. And the reason why I'm asking this question, because essentially in this case, you always assume that only curvature is physically observable. And what I'm saying that actually it is similar to Aronoff-Bohm effect. When you have topological effects, there is so-called holonomy. And in this case, not field, not F mu, but A enters the problem. So I send you my actually slide, which I recently discussed the vacuum energy and this linear part of H just in the chat. But nevertheless, my question is, let's assume that you have linear part of H. Does it change your analysis? So you answer the question and I sent my link.
Okay. I don't know. This equation is from the model of Solar.
Yes.
So I cannot tell you if adding H will modify and how it will modify.
Okay, let me tell you the long story about Solar. So essentially, we discussed that, and he cited my papers with the linear H, but nevertheless, he insists that because the curvature it's only H squared. Anyway, I send you the link to my recent talks in on cosmology, on quantum field theory at this part. So to demonstrate that topological holonomy effects always give you the linear terms as well. And we disagree with Solar on this part. So essentially, so you cannot immediately say what's happening with the linear term. How does it impact your analysis? So you cannot say right now, or you can.
No, actually, because we are not proposing this kind of model. We just variate Newton's constant at BBN. So at this point, we don't have a dynamic model for Newton's constant. So Solar and people, they have they have studied that, but we don't.
Yeah, okay. So just look and you will see that there is actually a term related to holonomy, to topology.
Okay, thanks.
Dionysus?
Yeah, actually, so I have a couple of questions if there is time. So, okay, so the first one is, so we see that the lighter elements are calculated nicely, right?
Yeah,
Right after PPN, but then the divergence starts with lithium. So I'm just wondering what's happening with beryllium, let's say, or even heavier elements.
Okay.
Is there
Well, Big Bang nucleosynthesis stop at atomic mass 8. So you will have some beryllium going on there, but it will decay to lithium. It's not so big, the abundance of beryllium.
Okay. Okay, thanks.
Yeah,
and
it's also more difficult to determine observationally the beryllium. So it's usually not employed in order to do this analysis.
Okay, thanks. And maybe a second question if there is time.
I can add actually to this answer. So essentially all heavy elements, they're not from Big Bang nucleosynthesis, they come from supernova or from somewhere else. So essentially beryllium or even higher elements, they're so small that you don't see them from Big Bang nucleosynthesis. You see it from somewhere else.
Okay,
that's absolutely correct. And for the final quick question from Dionysus.
Yeah, so maybe there is a slide called motivation for variation of alpha. Maybe if you could go there, Sebastian. Yeah. Yeah, so in the upper plot you show, so the idea here is that there is a spatial modulation of alpha in the early universe, right? And so I'm just wondering how that behaves today. Like, has that smoothened out? Or do we live in some part of the universe where is some alpha, but then somewhere else there is another alpha according to this model?
Yes, I think it is so. Maybe you may also ask to Flambon. I think he will probably talk about this. But I think the interpretation you do is okay. There were also some discussions about time variations of alpha. Some previous papers discussing that in the past there could be a smaller alpha, there could have been a smaller alpha, but actually this paper then was opening some controversy on that topic. So that's all I have to say. Yeah.
Okay, thank you.
I actually also have a similar question, but in the interest of time, if we have at the end, I might ask you after the end of the session.
It would be a pleasure.
So let's thank Sebastian for the nice talk. And our next speaker is Dave DeMille. Perhaps we can test the connection with Dave.
Yes. Can you see me and hear me now?
I can see you and I can hear you very well.
Okay, great. I will share my screen then.
Yes, please.
Okay, do you see my slides now?
Oh, perfect. I can see your slides, and if you could try moving your cursor as well, perhaps.
Yes, thank you. How's that?
Yes, I can see a red laser pointer.
Great.
Perfect. Whenever you're ready.
All right, great. I'd like to thank Evgeny and Victor for organizing this session. And today I'll be telling you about something that's a little outside the primary scope of the session, which are experiments that are probing TeV scale and even higher scales for new physics by looking for particle electric dipole moments. So I'll spend some time talking about the connection between the electric dipole moments of particles like the electron or the proton and new high scale physics, talk about generally how to go about detecting a signal like this, then spend some time on our experiment called the ACME that currently gives the best limit on the electrons EDM, a little about the interpretation of that in terms of theories of beyond the standard model physics, and then an outlook about what I see as a very exciting future for this part of the field. So the place to begin is to recognize that any particle, if it has an electric dipole moment along its quantized spin axis, that's evidence for CP violation. And one can think about this in a very simple cartoonish model. Suppose you have a particle with a finite size, here an electron with negative charge, assuming semi-classically that it's a sphere. If you add an electric dipole moment to that, then you'll get a charge asymmetry equivalent to a little bulge of charge on one end of the spin axis and a little deficit of charge on the other side. If you take a movie of this electron and do a time reversal transformation, of course, the spin direction changes, but the electric dipole moment direction is just a static charge distribution, so that remains unchanged. And if all electrons look like the picture on the top, then the picture on the bottom doesn't exist, and therefore time reversal symmetry is violated. And of course, in relativistic quantum field theories, we know that the combined symmetry CPT has to be conserved, and therefore T violation is equivalent to CP violation. So the EDMs that we look for are explicitly T violating, but I'll often use the language of CP violation since it's equivalent. And this picture also, or if electrons or any other particle have an EDM along their spin axis, that also violates parity. That's a little less important for this discussion. So it's been recognized for a long time that looking for, or the CP violation, understanding and looking for new sources of CP violation is a very powerful window to new physics. For example, we know for many decades now that CP is not a good symmetry of nature. Its breaking has been observed in K mesons, B mesons, D mesons. And so this is not, once the symmetry has been broken once, as we know it has been in the standard model, then there's every reason to believe that it will be broken again. And CP violation can always be parameterized in terms of a complex phase angle. So if this angle is 0, the CP violation is 0. But if it's pi over 2, then the CP violation is maximal within a given context. So all these observations with mesons are consistent with a single source of CP violation in the standard model. It's the complex phase that appears in the quark mixing matrix, the CKM matrix. And it's known from these measurements with K and B mesons that this phase angle is almost exactly 1 radian. So in no sense is the CP violating effect in the standard model intrinsically small, though it happens that the particular mechanism of entering through the quark mixing means that in most observables, the signal is small. But the CKM mechanism for CP violation is sort of peculiar, and in some sense it's minimal, in the sense that if you add new physics to the standard model, new fields, new quantum fields, new degrees of freedom, then it's very easy to introduce new ways to violate CP, or new degrees of freedom that include complex phases that there's no particular reason why they should be small. So in a fairly generic way, extensions to the standard model include these new sources of T or CP violation. And of course, in addition, we know that the baryon asymmetry of the universe from the old decades-old arguments from Sakharov require CP violation in addition to numerous other things. But we also know that the CP violation within the standard model is not nearly big enough to explain the degree of the baryon asymmetry that's observed. So not only does CP violation, it's not forbidden, we know we need more of it, and there are many ways to generate this in extensions to the standard model. This is all strong motivation to look for signals like this. The way EDMs are generated is as radiative corrections. So here's a very simplistic sort of cartoonish example of how, for example, an electron could acquire an EDM. It requires some sort of Feynman loop diagram with some new particle that includes a CP violating phase, here written as phi. And that particle has to somehow couple to electrons. Here it's shown coupling directly to electrons with some dimensionless coupling strength G, but it can also couple indirectly through 2 or more loop diagrams. If you draw a Feynman diagram like this, just simple dimensional analysis tells you that this can induce an electric dipole moment that depends on the coupling strength to the nth power, and there's the number of loops in the diagram. It scales like the inverse square of the mass of this new heavy particle and is the sign of the CP violating phase. And with natural assumptions, in particular, that the new phase is of order radian, just like the only CP violating phase that we know of so far in nature, that the coupling is roughly electromagnetic strength, and that the new particle is not too far above the electroweak scale, say with a mass of a TeV. This hand-waving dimensional estimate would lead you to conclude that the electric dipole moment should be already about 30 times larger than the current bound that our experiment puts on. So this is a clear signal from the beginning with a very simple argument that these experiments are already probing new physics in a powerful way. Of course, in the standard model, there is CP violation, and that CP violation does induce an EDM of the electron and other particles. But in all cases, the standard model prediction for the EDM is orders of magnitude below current sensitivities. So for the example of the electron, the EDM appears, a non-vanishing EDM appears first at 4-loop order. And even in this fourth order Feynman diagrams, the sum over all of the diagrams has big cancellations due to the Jim mechanism, essentially the flavor symmetries built into the standard model. So that means that looking for EDMs is a background free probe of new physics still for many orders of magnitude, for the electron about 9 orders of magnitude, for neutrons and protons it's more like 6 or 7 orders of magnitude before we hit a standard model background. So by contrast, in theories that extend the standard model, for example, the most naive versions of supersymmetry, it's quite possible to introduce an EDM at 1-loop order via direct coupling and with CP violation arising from supersymmetry breaking physics. And there's no particular reason why this should be canceled or suppressed in any way. So many of the bounds that I'll talk about are discussed in the context of supersymmetry, but I'll just emphasize that supersymmetry is really just one example, that it's really quite common for models that introduce any sort of new physics, not just supersymmetric partners, but also extra Higgs doublets, leptoquarks, and so on, to introduce new CP violating phases and therefore new mechanisms to generate EDMs of the electron and other particles. So start to tell you about how we do look for these EDMs, but I'll just pause to point out just how sensitive these measurements are. In order to get a sort of visualization of this, if you think of an electron, of course, in quantum field theory, the electron is a perfect point particle with no size. But there is a definite size scale, length scale associated with a cloud of virtual particles, in particular virtual photons around the electron that give rise to the G-2 factor of the electron. And that size scale is about 10 to the minus 13 centimeters. So if you scale that up to the size of the Earth, then the size of the EDM that we would have detected in our ACME experiment that I'm just about to tell you about would correspond to taking a slice 2 nanometers thick off the southern hemisphere of the Earth and pasting it on the northern hemisphere. So these are extraordinarily sensitive experiments. Well, both terrifying and fun to work on. So the general idea of looking for an EDM is similar in almost all experiments. You start with some collection of spins in unknown directions. You apply some sort of optical pumping or laser state transfer technique to transfer the polarization of the laser beam into a distinct polarization of the electron or proton or whatever particle you're interested in. If you polarize the particle sideways, that's a superposition of spin up and spin down. For technical reasons, these experiments almost always include a magnetic field that exerts a torque on the magnetic moment of the particle and causes it to precess around at frequency omega. That precession is equivalent in every way to the energy splitting h bar omega between spin up and spin down. And you can think of these experiments as magnetic resonance type experiments that are looking at this spectral line associated with a spin flip that gives you some peak in a signal at the resonant frequency. So now if you apply an electric field parallel to the magnetic field, if the particle has an electric dipole moment along its magnetic moment, then it'll exert an additional torque, cause a faster spin precession, or equivalently a bigger energy splitting between spin up and spin down, correspondingly shifting the spectral line to higher frequencies. And then you can reverse the electric field and everything changes sign, the spectral line shifts to lower frequencies instead. So with this simple picture, it's easy to write down a figure of merit for statistical sensitivity in experiments of this type. That's just the energy shift over the energy resolution. And you conclude that you want the biggest electric field possible, the longest coherence time possible, the highest counter rate possible, and of course, the longest experimental integration time. So let me tell you now about our ACME experiment, a collaboration between my group previously at Yale, now at the University of Chicago, John Doyle's group from Harvard, and Jerry Gabriel's group from Northwestern, where we've managed to maximize many of these critical parameters. Here's the team of students and postdocs who did all the hard work to actually do the measurement in our ACME 2 experiment, where the result was published in 2018, and then the three leaders of the experiment. So there are a few key aspects of ACME that we take advantage of. One is we embed our electrons inside the polar molecule thorium oxide. Very, very roughly speaking, the advantage of the molecule is that by applying a small laboratory external field, you can completely polarize the molecule. And then inside the molecule, the electron, which spends a lot of its time between the oppositely charged ions, is acted on by a much larger effective electric field due to its relative motion. And in fact, the correct number for thorium oxide is about 80 gigavolts per centimeter. In practice, we only have to apply some tens of volts per centimeter to polarize this molecule. And in exchange, we get this 80 gigavolt per centimeter effective field acting on the electron EDM. Unfortunately, this requires having a molecule that has at least one unpaired electron spin. And this was a big impediment to the field for a long time, since these are chemically free radicals. A key aspect of being able to create beams of free radicals or other molecules is this technique of hydrodynamically enhanced cryogenic beams, pioneered by John Doyle's group at Harvard. The bottom line here is these beams give you about 1,000-fold greater brightness than other sources for the sorts of difficult species that are needed for EDM experiments. The particular choice of thorium oxide had a number of benefits, and here's the electronic structure of thorium oxide. It's actually not a free radical. Its ground state is a closed shell state with paired off electrons in a singlet state. But the first excited state is a metastable state with two unpaired electrons in a triplet configuration. Our molecules start in the ground state. We apply lasers to transfer them into the metastable triplet state. Then we can probe both polarize the electrons in the state and then later probe their polarization using laser-induced fluorescence, as shown here. So there are lots of advantages to doing the experiment in this particular state of this particular molecule. In addition to the large effective internal field, this thing has a long lifetime, allowing long coherence time measurements. It also has a suppressed magnetic moment that suppresses magnetic noise and systematic errors. And I'll explain on the next slide another advantage called the omega doublet comagnetometer. But technologically, this proved to be an especially easy system to work with. This feature that I mentioned on the last slide, the so-called omega doublet comagnetometer, is associated with a structure of molecules that is not terribly familiar to people outside the world of molecular physics. But the idea is when you have an electron spin triplet that can have spin down, up, or sideways, then there are two mirror image copies of a molecular state where the spin is either along the molecular axis or against the molecular axis. One can construct parity eigenstates, which are the true energy eigenstates of this system, by having even or odd combinations of molecule along or against the spin axis. But when you apply an electric field to polarize the system, you get an energy level diagram like this as these states mix and repel from each other. Then you can do the experiment in this pair of states, just as I described before, create a superposition of spin up and spin down, and look for the precession of the EDM in this effective electric field internal to the molecule. And you can flip the electric field just as I described before. But in addition, instead of doing this measurement, you can tune your lasers to prepare and probe this pair of states instead, where everything is identical. You can again make a superposition of spin up and spin down, except that the effective electric field of the molecule is in the opposite direction. In this pair of states, the molecule is polarized in the natural direction along the electric field. In this upper pair of states, the molecule has polarized in the unnatural direction opposite the field, which is why it had to go up in energy. The bottom line is that this comparison of the signals in these two different molecular states allows us to cancel a huge range of otherwise difficult systematics in our experiment. So here's a schematic of the ACME experiment. We start with this molecular beam source. Molecules are cooled to a single rotational level with lasers and microwaves. They enter this interaction region where lasers spin polarize or populate and then spin polarize the triplet state. They then fly for about a millisecond in the presence of parallel electric and magnetic fields. And then finally, we use polarized laser light to read out their final spin orientation. That was the schematic of the first generation of ACME. The second generation, which is the last we published a result from, increased signal by opening up the molecular beam, preparing the molecules more efficiently, and then detecting them more efficiently. Here are some pictures of the apparatus: transparent electric field plates, cryogenic beam source, main vacuum region, magnetic shield end caps, magnetic coils shown with the scale in LHC units here. The whole magnetic shielding symbol system buttoned up. We have a few tables full of lasers and optics, as is typical for modern atomic physics experiments, and very modest control room shoved in the corner of the lab. And here are pictures of a few of the ACME students in the lab with the main apparatus. So with this apparatus, we generate signals like this that show the electron spin angle as a function of a control parameter such as the magnetic field. Essentially, we park the parameters of the experiment around here, then start flipping the electric field back and forth and look for the signal to ride up and down the slope on this curve, synchronously with the electric field or the molecular polarization. As promised, we flip things.
You have 10 minutes.
Often. Okay. Thank you, Evgeny. We flip things often, both the internal polarization and the electric field. And then we take the phase angle, essentially the angle at which the electron spin ends up in the experiment, and take all of our data and rewrite this data in an expansion where we look at how the different components of this phase angle change under reversals, like reversing the electric field or the magnetic field or the molecular polarization or both. These different switch correlated phases isolate different physical contributions to the total phase signal that we see. This one, for example, that flips when we flip the molecular orientation and when we flip the electric field is the signature of an EDM. And all these other switching contributions end up serving as diagnostics for systematic errors that we study in great detail. If we look at this EDM phase, our data analysis is not very sophisticated. We take a histogram of all the EDM phases, we fit a Gaussian to it, do just a little bit of beyond undergraduate level statistical analysis to find the mean of this distribution with an uncertainty of about 3 × 10⁻30 e centimeters. And then I won't go into details, but by looking at these other correlated phases, switch correlated phases, we're able to quantify and understand our systematic errors. The possible shifts due to all the systematic errors that we investigated were all consistent with 0. The total systematic uncertainty was a little below the total statistical uncertainty. And these are all given in microradian per second frequency units. So the bottom line is that we got a number for the electron EDM that was consistent with 0. And that allowed us to set the world's best limit on the electron EDM. Its magnitude has to be less than 1.1 × 10⁻29 e centimeters. So this shows a first view of what this means. So on the x-axis here is possible values for the electron EDM in a log scale. Splotches of colors are very, very rough depictions of the range of predictions in various different models that extend the standard model. Most of these shown in blue or in green are supersymmetric models. Green are new versions of supersymmetric models that have become favored after the LHC has not been seeing superpartner particles up to the energies they've probed so far. And this is our latest ACME limit. There are a few different ways to look at the impact of these measurements. Here's a nice plot from a review about the idea of naturalness, which is a strong motivation for supersymmetric extensions to the standard model. And naturalness has different meanings to different theorists, but here's a sort of typical plot that shows possible superpartner masses on the Y scale, the heaviest standard model particles, all the possible supersymmetric partners of the standard model particles. And the green lines show roughly where one would expect particles to be in order to satisfy a naturalness bound. I updated this a couple of years ago to show that the LHC is obviously making progress, probing higher mass scales. If you look at this same plot, then our ACME-1 experiment was already setting interesting limits, as was a complementary experiment looking for the nuclear EDM, roughly speaking, the nuclear shift moment of mercury 199 in an experiment using atoms. Our ACME-2 result now pushes our sensitivity for the case where there are maximal CP violating phases in the supersymmetric model up to limits that are well above sort of typical naturalness bounds and also far beyond not only where the LHC has already reached, but where they hope to reach. And there are different bounds on different kinds of particles because of the different mechanisms that would lead those particles to induce an electron EDM. For example, there's a simple one-loop diagram that can induce an EDM by coupling the electron to a selectron, two-loop diagrams that couple the electron to top squarks and top quarks, Higgs Zenos, and so on. And then in models where there's flavor violation turned on, here, these models assume minimal flavor violation, no flavor violation beyond the standard model. But if you allow new flavor violation to be associated with the supersymmetric particles, you can even set limits for maximal CP violating phases up to over 100 TeV. And similarly, we're not just sensitive to the electron EDM, but also to some types of electron nucleus interactions, such as would come about due to scalar leptoquark exchange. And here we're sensitive in some models to leptoquark masses up to 1,000 TeV, so a PeV. We're now constructing ACME3 with lots of big improvements. The bottom line is that we anticipate a factor of 10 to 20 improved sensitivity with results coming out around 2024. So stay tuned for this. Here's the ACME3 team, same old folks, but some new students and new collaborators from Okayama University in Japan. But motivated by the success of ACME, we've now launched the Centrex experiment, which is a new molecule-based search, not for the electron EDM, but for the nuclear shift moment, which you can think of roughly as a nuclear EDM. The idea is the same, that inside the molecule, the nuclear EDM feels many orders of magnitude stronger effective field than in the nucleus of an atom or inside a neutral atom like mercury 199. We can also use the fluorine spin as a co-magnetometer to suppress systematics. And there are some nice features of this particular molecule. So our goal here is now to be sensitive to hadronic CP violating interactions up at the multi-TeV scale. Here's a schematic of the experiment. It looks a whole lot like the ACME3 schematic. So we're using a lot of the same techniques. And with possible upgrades by laser cooling the molecules in Centrex. Here's the Centrex team, again, a collaboration between a couple of PIs, Dave Kawal from UMass, Tanya Zelevinsky at Columbia, Steve Lamoureux at Yale, Larry Hunter at Amherst, in addition to myself and our students and postdocs. The bottom line is with Centrex, we project a sensitivity that's to the proton, or generally speaking, isospin combinations that are proton-like, that are a factor of 10 or so better than current limits. And right, so here we're anticipating results again around 2023 or 2024. But in the meantime, there's a real ongoing revolution in this field, which is associated with the ability to cool and trap the kind of molecules that are interesting for EDM experiments. So there are experiments such as ones that my group has pioneered, and now the capabilities in several other groups to directly laser cool molecules with unpaired electron spins. But then a whole different class of experiments where it's been possible to assemble molecules from laser-cooled ultra-cold atoms. And these assembly techniques are really spectacularly successful, making it possible to have molecules with temperatures as low as 50 microkelvin all the way to quantum degeneracy. Sort of exciting vision for where this is going, we think in the very near future, is to do, for example, a shift moment experiment with a particular molecule that can be assembled out of ultra-cold atoms and held in an optical lattice with parameters that have already been demonstrated with analogous other molecules made out of different alkali atoms. We would project about a 300-fold improvement versus the mercury current bounds on the nuclear shift moment. And this is just with things that have been achieved already. There are similar gains projected for electron EDM experiments with directly cooled species, and the potential for even more improvements in the long term by employing spin squeezing to reduce the noise below the standard quantum limit, which is achieved in most of these experiments. So that's the end of my talk. Thank you for listening, and just point out that experiments that are already underway are going to be probing extremely high energy scales, far exceeding the reach of the LHC, as long as there is strong CP violation associated with the new physics. And there are also very plausible ways to keep advancing the field by many orders of magnitude in the future, if needed. That is, if we don't see an EDM in these ongoing generation of experiments. And it seems more and more plausible to be able to really probe deep into the PeV scale with these experiments in our lifetime. With that, I'll thank you for your attention.
Thank you very much, Dave, for the very nice talk. Are there questions? I actually have a question. So with the Centrex experiment, what is the experimental state that you want to use in the thallium fluoride?
Yeah, so in thallium fluoride, we're using the molecular ground state. So it's a closed shell singlet sigma state. Thallium fluoride is chemically stable. And there we effectively can have, a pseudo infinite lifetime. Right, the interaction time will be about 3 times longer in Centrex than it is even in ACME 3, where we've extended the time compared to ACME 2. But that starts to reach something close to a limit for what you can usefully use for an interaction time in a beam experiment.
And so your main sensitivity to hadronic CP violation would be through the nuclear shift moment, presumably then.
That's right, yeah. So thallium has spin 1/2, and yeah, we have no unpaired electrons. So it's really the shift moment, which is our primary sensitivity. That's right.
Any other questions?
Yeah, I actually have
be honest, please, yeah.
So I'm wondering about the experiment, the prospects of carrying out the experiment involving francium. So could you go to that slide, please?
Yes.
Okay. So the first question is very simple. What's the molecule code? Francium silver. Okay.
Francium silver. Yes.
Okay,
yeah.
good enough.
Sounds insane, but yeah.
Okay. But okay. Yeah. The more important question is how do you get access to such a molecule? How do you produce it, and for how long? How much time do you get in the machine every year?
Yeah. So right. So the idea is to take advantage of these techniques that take laser cooled atoms and assemble them to form molecules. Those methods are extraordinarily efficient. Essentially, they turn atoms into molecules with efficiencies of order 70%, 60%, something like that. So really, what you need is the atoms. Both francium and silver atoms have been cooled and trapped in magneto-optic traps. They both have alkali-like structure. No one's bothered to try to make quantum degenerate gases of them because there was no good reason to before, and they're not the easiest things to work with. But we see no reason why they shouldn't work just like every other alkali for that purpose, though it will require a lot of data about scattering properties and such. And francium, the state of the art now is that accelerators and actually even offline experiments, people are able to to get order 10 to the 5th francium atoms in a mott. And that's with much shorter lived isotopes than this. So it turns out francium-223, which is nice because it has an octupole deformation that enhances the shift moment by a factor of 100 or a few hundred, is also the longest lived francium isotope with a half-life of a whopping 22 minutes, which doesn't sound great, but it's a lot better than the couple of minutes for isotopes that have been used up to this point. And then finally, francium-223 is the daughter of long-lived actinium-227, which is actually made in massive quantities for medical applications. So simply by taking a big piece of this actinium-227, which we know that we could purchase, and milking the francium out as a daughter continuously, we can get, I don't know, something like a million, well, with the efficiencies that have been seen in similar experiments with other molecules, we anticipate getting 1 million molecules every 10 seconds, something like that.
Okay.
So,
Okay, so
this 10 to the 4th is pretty conservative.
Okay, so the important thing is you don't need to be stick the experiment right next to the machine to acquire francium. You get it from.
That's right.
Okay. Okay. Thank you.
Yeah, that's right. Yep. At least that's the idea in principle, but people have actually done that with another isotope of francium already a couple of times. So we feel confident we can do it with this isotope.
And I guess we have time for one final quick question, if anyone has one. Well, I don't see any more questions. So with that, I would like to thank Dave and all of the other speakers in this session for the excellent talks. And thank you all very much for sticking to the time. We actually did just get I got a notification that it's going to shut down automatically in 4 minutes. So luckily it didn't shut down automatically during Dave's talk, so everything went well. So I guess we still have, in principle, 4 minutes for discussion for any other questions, which may be questions to some of the other speakers that somebody may have had. I actually had one question to Sebastian earlier. It was related to one of the questions that Dionysus asked with this spatial variation in alpha. And I was curious, with this Hubble constant data, for example, from the early times of the universe, so high redshift, early redshift, is there any evidence for a spatial anisotropy in the H0 data? Or is it just purely sort of a temporal variation between a discrepancy for high redshift as opposed to low redshift measurements?
Sorry, I had some problems with the connection. May you repeat?
I was basically just asking, with the H0 tension, is there any spatial anisotropy in any of the data sets at high redshift or low redshift?
Well, usually the late time measurements are the direct ones, and the early times are the indirect ones. Was that your question?
It's related to that, but in, for example, the low redshift measurements, there's no spatial anisotropy.
Okay. I haven't seen that kind of studies. It could be a nice question. I don't really know.
Oh, okay, I see. Thank you. I guess there's time for one more question to any of the other speakers, if there are any. Oh, and before we do that, I'd just like to also mention that tomorrow we will resume at 9:30 Central European Summer Time. So we'll have another session tomorrow. Okay, well, it looks like there's no more questions. So thank you all very much for joining us today, and I hope to see you all tomorrow. So thank you very much. Bye-bye.